Hola, ¿qué tal? Otro día más, aquí estamos en Visiting Spaces, en Maker FAIRE Girona. Soy César García y estoy encantado de daros la bienvenida a un día más repleto de actividad, repleto de proyectos y, como siempre, con la información y los proyectos más punteros para que podáis estar pendientes de todo lo que ocurre ahora y el futuro, hacia dónde vamos. Y precisamente vamos a hablar hoy con Quim de Ciurana, que es catedrático de la Universidad de Girona en el área de Ingeniería de los Procesos de Fabricación desde el año 2009. Estamos aquí ya con Quim, que nos va a hablar sobre un proyecto de oncología y 3D, pero antes, como siempre, vamos a ver este vídeo en el que se resume su proyecto.
Vale, perfecto.
Pues nada, ahora ya Quim a la vuelta, ya ahora se está poniendo. Bueno, pues ya hemos visto este vídeo de Onco en 3D, un proyecto en el que participa Quim desde la Universidad de Girona. ¿Qué tal, Quim? Bienvenido a Maker FAIRE.
Hola, ¿qué tal, César? Muchas gracias por invitarme.
Encantado de descubrir nuevas aplicaciones de la impresión 3D. Normalmente los makers siempre inventan cosas con la impresión 3D y quizás nos podrías explicar en más detalle esto que hemos visto en el vídeo, ¿no? Hemos visto ahí una célula que se movía, que se escapaba, ¿no? Y como esa estructura que permitía, bueno, pues trabajar con ella de una forma particular. ¿En qué consiste este proyecto?
Bueno, antes me voy a salir un poco del guión, César, si me permites.
Perfecto.
Porque, bueno, cuando me invitasteis tuve que escoger uno de los, digamos, muchos proyectos que manejamos aquí en nuestro grupo de investigación. En todos ellos, un poco la idea es el uso de esas tecnologías de fabricación aditiva, también conocida, digamos, coloquialmente como la fabricación o impresión en 3D. Y, bueno, desde fabricar prótesis de tráquea, prótesis de rodilla, prótesis de fémur, pero también, bueno, pues stents cardiovasculares. Uno de los proyectos en los que vi la posibilidad de ser más atractivo es el del onco en 3D, porque lo que hemos hecho es juntar la tecnología, ¿no?, de la fabricación aditiva con las necesidades médicas que hay hoy en día en el mundo del cáncer, ¿no? Y en concreto, un poco eso que me preguntas, pues la idea era, hasta ahora la investigación, digamos, oncológica, lo que hace es intentar estudiar las células, pero se hacía en el plano, con las cápsulas de Petri. Lo que en cierta manera vimos que no corresponde a una realidad, porque las células viven en el cuerpo humano, con lo cual, ¿no?, o sea, viven en un entorno, digamos, de 3 dimensiones, y lo que se llama la matriz extracelular, pues también es de 3 dimensiones, con lo cual usamos esa idea bueno, se denomina scaffold en inglés, porque el nombre es como mucho más, digamos, atractivo, pero en realidad estamos hablando de andamios, ¿no? O en catalá, bastidas. Y eso lo que permite, pues, es crear estructuras de 3 dimensiones, tridimensionales, en las cuales las células, pues, se comportan como en la realidad. Y eso nos permitirá, pues, ver que en su comportamiento con la realidad, si las células malas, digamos, vencen a las células buenas, y si los posibles tratamientos que se puedan desarrollar funcionan bien o no funcionan bien. Y es un poco el objetivo. No me enrollo más porque
no, es muy interesante
y tenemos tendencia a alargar las respuestas, ¿eh?
No pasa nada aquí. Una cosa que me llama mucho la atención, ¿no? Trabajamos con impresión 3D que tiene unas resoluciones que entiendo que a la hora que, digamos, condiciona los diseños a la hora de modelar, ¿no? A la hora de modelar zonas del cuerpo, partes del cuerpo a escalas distintas. ¿Cómo es ese proceso de...? Claro, no sé, esto es una pregunta desde el total desconocimiento. ¿Escaneáis la superficie celular o buscáis... ¿Cómo hacéis ese encuentro entre lo 3D y lo orgánico?
Pues mira, es una pregunta que nunca me había planteado. Voy a intentar resolverla. De hecho, el scaffold o el andamio sigue inicialmente sigue una estructura regular. Y precisamente ahí está un punto importante, un punto clave. Es decir, nosotros hemos creado diferentes estructuras regulares y hemos tenido que comprobar esas estructuras regulares si respondían a una buena unión con la célula o no. Es decir, si las células se encontraban en un hábitat cómodo con una determinada estructura, pues crecen, se desarrollan, se multiplican. Si la estructura es regular, pues deja, digamos, demasiados huecos. De hecho, esto se llama el coeficiente de porosidad. Las células no consiguen reproducirse, no consiguen engancharse, con lo cual mueren. Entonces, como tú bien dices, no estamos creando un entorno 3D apropiado para ese tipo de células. Lo que queremos es que las células se crezcan y se reproduzcan, si no, no estamos consiguiendo lo que queremos. Y eso nos ha dado un dato también interesante. Diferentes células se comportan diferentemente en esa estructura del andamio, con lo cual no hay un andamio único, sino que hay un andamio que depende del tipo de células que tú quieres estudiar o tratar.
Eso es muy interesante. Yo entiendo que ahí el potencial real, ¿no?, de la fabricación aditiva es la capacidad de prototipar y probar de forma rápida y ágil, ¿no? Puedes cambiar diseños, evaluar, descartar, ¿no?, de una forma bastante adaptada a cada caso, ¿no?
Sí. O sea, precisamente cuando de alguna manera se originó como grupo de investigación, trabajamos, de hecho, el proyecto Oncon 3D es una unión de 2 grupos de investigación, el que yo estoy liderando, el GREP, más tecnológico, y Targets Lab, que es un grupo de investigación de la Facultad de Medicina, también de la Universidad de Girona. Entonces, el arranque, la idea fue, por un lado, el hecho de copiar, mimetizar lo que es esa idea de 3 dimensiones que necesita la célula para vivir, es su medio natural, con esa idea de poder personalizar de forma muy rápida ese posible entorno, porque la célula era diferente, ¿no? Cosa que en el estudio 2D que se venía haciendo, pues era mucho más lento. Es decir, el 3D lo que nos lleva es mejorar la respuesta en tiempo de lo que nosotros queremos para diferentes células y diferentes tratamientos. Cuando hablo de tratamientos ya me refiero a uso de fármacos, ¿eh?
Hay una cosa que yo creo que es como la siguiente frontera, ¿no? Porque veíamos ahí la impresión 3D, que estábamos trabajando con impresoras de extrusión de filamento, y nos hablas antes de otros casos muy interesantes también, como todo el tema de prótesis, todo el tema de ayudas, por ejemplo, en quirófano. No sé si de todos esos campos, ¿cuál crees que ahora mismo va a tener más impacto a corto plazo, que ves que ya está, que a lo mejor no somos conscientes desde fuera del ámbito hospitalario, pero que dices, esto ya va a ser el día a día, ¿no? Como que hay tal cambio. ¿Cuál destacarías de todos esos casos de la impresión 3D en el uso hospitalario como más interesante?
Bueno, el que en este momento tiene más interés por un tema de, digamos, a ver cómo, o sea, si me pongo todo lo que es el campo de las prótesis o los implantes, la impresión 3D sin duda es una herramienta fundamental, pero ahí topamos con lo que podríamos decir la reglamentación. Dicho de otra manera o ampliando, cuando tú eres capaz de personalizar rápidamente una prótesis para una determinada persona, lo que te queda por ver es si ese resultado, producto, esa prótesis es implantable, tiene que haber pasado unos exámenes. Entonces, aún hoy en día, esa tecnología no ha conseguido romper las fronteras de lo que serían las diferentes regulaciones de los diferentes países. Se está avanzando y se ha avanzado. En cambio, cuando empezamos a hablar de lo que es el estudio en quirófano, y de hecho los cirujanos son actualmente los grandes usuarios de esa tecnología, les permite realizar un entrenamiento muy real de lo que se encontrarán antes de empezar a abrir el paciente, ¿no? Es decir, con un MRI o un escáner del paciente puedes crear ese cuerpo 3D y puede probar cómo será la cirugía antes de realizarla. Y es un tema que no necesita regulaciones porque, en definitiva, incluso el material puede ser no compatible porque lo haces en el despacho o en el laboratorio. Y ese es uno de los elementos que actualmente está en uso y es el campo que se lleva más, ¿eh? Pero bueno, no estamos lejos, por ejemplo, en materiales que sí están muy probados su biocompatibilidad, como sería el titanio, sus aleaciones, ya se hacen prótesis de mandíbula. Existen también los elementos dentales ya hechos con esas aleaciones, con lo cual ya se han superado las regulaciones de material y el hecho que la tecnología sea diferente no implica.
Sí, ahí justo con todo lo que ha pasado con el COVID, una de las cosas que descubrimos imprimiendo cosas, ¿no? Que parte de la regulación y parte de las reglas, que desde el punto de vista maker eran más complicados, todo lo que tenía que ver con la fabricación en hospital de producto médico personalizado, todas esas fronteras que por la Unión Europea había plan para este año cerrar y cambiar la regulación y han dicho, a lo mejor este año no es bueno, a lo mejor hay que pensar a futuro. ¿Cómo, desde el punto de vista de la investigación, cómo veis o sea, entiendo que hay que estar como siempre entre la técnica, lo que permite la técnica y lo que permite también la regulación, ¿no? Estáis como en esta zona central, ¿no? Siempre tratando de buscar algo que satisfaga ambas partes, ¿no?
Sí, lo que pasa que ahí la técnica o la tecnología, desde mi punto de vista, poco puede hacer. Es decir, la tecnología o el producto diseñado llega al punto y al estadio en que se consigue pues, que cumpla una serie de requisitos, digamos, de propiedades mecánicas de resistencia de fuerza, de fatiga, de dureza, de precisión dimensional, etcétera, etcétera. Eso se puede comprobar. Pero las regulaciones lo que quieren comprobar, incluso nosotros hemos llegado a hacer, perdona, me salto un poco antes, nosotros hemos llegado a hacer estudios de degradabilidad para saber eso dentro del cuerpo humano, cómo se puede comportar, pero aún así, esas pruebas son esas pruebas que se llaman in vitro. Lo que falta es todo el desarrollo de las pruebas in vivo y eso, claro, la regulación pues requiere de un tiempo. De hecho, mira, lo que dices tú como paralelismo, lo que estamos encontrando en las vacunas, ¿no? Todas esas vacunas que están apareciendo en las noticias, pues que no se están implantando porque están en lo que se llama la fase 3. Y esa fase precisa de unos tiempos, porque hay que ver qué resultado tiene ese elemento en una implantación de cuerpo real. Entonces, ahí la tecnología, pues, poco puede hacer para acelerar esa fase 3, porque esa fase 3, pues, no es más que el cuerpo humano, en definitiva.
Y los tiempos y el cuerpo humano cambian menos que la tecnología.
Sí.
No nos podemos de momento imprimir, aunque ese es otro tema que siempre que se habla del tema de salud, de hecho, justo hay muchas pruebas que hablabas antes de in vitro que se estaban haciendo con laboratorio, con todo el tema de impresión bueno, supongo que serán también scaffolds o andamios para imprimir con microfibras para células madre, y todo el mundo ve como en el futuro, así un poco como Star Trek, vamos a poder imprimir órganos, ¿no? Sí que hay orejas, hay zonas de cartílagos, zonas más blandas. Tú que estás ahí como en la primera línea de batalla de esta cuestión, ¿cómo lo ves? O sea, estamos en ese punto de que va llegando, se va avanzando en determinadas áreas, hay otras que tienen retos súper extensos para órganos a lo mejor que requieren mayor, no sé, por el corazón, por ejemplo, se lo ve como una cosa como muy ciencia ficción. ¿En qué punto crees que estamos ahora mismo?
Mira, yo soy ingeniero, ¿no? Y además soy ingeniero mecánico y o sea, muy tradicional en esas cosas, con lo cual, es decir, cuando una cosa es hierro, ¿no? Y cuando una cosa la tocas y se mueve o no se mueve. Entonces, tengo que decir que es verdad que hace unos años atrás, y te hablaría de unos 10 años atrás, eso que tú acabas de contar, muy bien, lo ves como una utopía o algo imposible, ¿no? O sea, de las películas de Misión Imposible y poco más. Pero yo he visto cosas que no, o sea, estamos en 10 años, he tenido la oportunidad, como dices tú, de ver cosas que son increíbles, ¿no? Y de hecho, pues bueno, ya ha habido como una estratificación de los problemas que poco a poco han hecho que se vayan superando obstáculos. Por ejemplo, se divide entre lo que se llama tejido duro y tejido blando, ¿no? O sea, tejido duro, por ejemplo, sería un hueso y que tú puedes realizar pues un elemento pues fuerte, digamos, de material consistente, que lo puedas implementar como si fuera un fémur, pues eso ya se hace. Con lo cual, digamos, la frontera del tejido duro ya se ha hecho. Luego viene el tejido blando, ¿no? Lo que decías tú, cartílagos, pues ya se está empezando a hacer también y ya se hace. Y quedará esa función, digamos, en según qué casos, digamos, motriz, ¿no? Y de hecho ya creo que, mira, no te sé situar, no sé si hace un año o 2 años ya se hablaba que en Israel se había hecho una primera implantación de un corazón. Obviamente, era un corazón, pues era un pequeño dispositivo que lo que hacía era realizar la función de bombeo. Y estaba funcionando. Y se había hecho un corazón debidamente personalizado para las características que precisaba esa persona humana, ¿no? Ese cuerpo humano. Con lo cual, pues yo cada vez soy menos escéptico al respecto, ¿no? Y he visto máquinas, pues eso, que como dices tú, y se llaman biocell printing, que, bueno, lo que hacen es empezar a imprimir células. Igual, pues no estamos tan lejos de tener la impresión de un dedo y que tenga no solo su componente estructural, sino su componente morfológica.
Qué interesante todo esto que nos cuentas, y creo que es muy, muy potente también ver que, claro, ahora todos los jóvenes que vienen ya con formación en 3D, con formación en toda esta parte, me encanta pensar hacia dónde podemos llegar. Nos queda un minutín. Kim, no sé si quieres compartir alguna cosa más antes de acabar.
Ya, porque yo no quería compartir nada, pero ya que lo has puesto tú encima de la tela, lo comparto. O sea, insisto nuevamente, yo soy ingeniero y soy de aquellos que me educaron o me formaron, ¿no? para diseñar, calcular y recalcular y comprobar. O sea, antes de hacer, calculamos lo indecible. En cambio, pues sí, la gente joven se atreve, ¿no? a ese tema de causa y error. Yo no digo que la ingeniería tenga que desaparecer, pero el 3D está permitiendo el atreverse. Y eso es una cosa que me fascina. En mis alumnos, incluso incluso tengo hijos que ves, ¿no? O sea, y dices, caray, es un cambio de paradigma y, bueno, pues la gente como yo tendremos que hacer un esfuerzo de decir, lo tenemos que aceptar. Yo de hecho lo he hecho, y lo acepto encantado y disfruto con ello.
Pues hay que probar, hay que ponerse manos a la obra. Gracias, Kim, por tu tiempo, gracias por acompañarnos aquí en Maker Faire Girona. Vamos a seguir con una tarde muy activa también. Estamos pensando en el futuro y ahora tenemos un panel que se llama Space, Tecnologías Espaciales para un mejor futuro en la Tierra. ¿Cómo puede influir todo lo que diseñamos para el espacio para el día a día de lo que hacemos aquí? Así que nada, no os perdáis el panel. Gracias a todos por seguirnos y volvemos a la vuelta cuando es 9:10 desde el Barcelona Supercomputing Center para seguir explorando todo este futuro de las nuevas tecnologías y cómo nos influye en el día a día. Saludos, Kim, saludos a todos. Nos vemos a la vuelta.
Muchas gracias. Muchas gracias.
Hi, everybody, and thanks for joining us in this space panel, where we will be talking about how space technologies can help solve Earth's challenges. Probably since we started looking at the sky and feeling curious about what those shiny dots were, we have been taking profit of what we've learned about space. For instance, during centuries, we used those glittering dots as a guide to travel. More recently, the development of space exploration technologies has benefited Earth and us humans in many, many ways. Maybe the clearest example are communications or the GPS, but also space technologies are helping us cope with other major Earth challenges, such as climate change, humanitarian crises, and mass migrations, just to name some. Moreover, in the next 20 years, we will see a huge transformation in more advanced space technologies. For instance, satellites that are already playing a big role in improving the state of the world will do even more as we launch satellite fleets, these mega constellations that are expected to create higher speed internet, for instance. Also, we will further explore the cosmos. We will go back to the moon, we will visit the red planet, and we are already planning to install a human permanent base in both worlds. For that, we need more innovation, new technology that will help us travel longer distances and adapt to hostile worlds. And for sure, while we prepare that long journey, all the technologies that will be developed will be used also to enhance our society and eventually to safeguard our planet. In fact, space technologies and research can be used to address the Sustainable Development Goals adopted at the United Nations 5 years ago. To talk about how we can use space technologies to get a better future on Earth, 5 brilliant minds will join us. The first beautiful mind will talk about how space technologies, since recently only reachable for space agencies and costing huge amounts of money, nowadays have been democratized. Rafael Jordà, who is the founder and CEO of Open Cosmos, a company founded in 2015, delivering satellite-based solutions designed to tackle Earth's biggest challenges. Jordà is an expert in space technology, and before creating Open Cosmos, he worked at Airbus, and even before that, he took part in some really innovative startups related to space tourism. Rafael?
It's a pleasure to be with all of you here tonight, and it will be a delight actually over the next 10 minutes to be able to share a little bit about our story at Open Cosmos and how actually we help democratize access to space. Let me share with you my slides so you can follow the journey that I have been mentioning. So most of you might think that a space technology, when you hear space technology, probably you think about complexity, about something that it's only for a few brilliant minds that are somewhere there in NASA or somewhere there at the European Space Agency. And we need to stop thinking like this. A space technology is just another technology that each one of you can use actually to solve big global challenges. Over the last decade, actually, there has been a massive disruption in this domain, very similar to the one that 50, 60 years ago, we started seeing in computers. On the top of the screen, actually, you see the evolution that the big mainframe computers had when they went into being smaller PCs. That was the democratization that happened. They became available as a tool for many to be used. And thanks to that, we started connecting those computers, developing the internet and all the applications that we now know, right? That's exactly what's happening right now in the space industry. We no longer need to spend hundreds of millions and wait for tens of years to deliver and to grow one of these big satellites. There is the possibility now, following standards and following advanced techniques and miniaturization, to develop smaller satellites that can still fly very meaningful sensors to basically disrupt a new wave of applications. And those applications, many of them are absolutely critical to solve some of the big global challenges that we need to address. At Open Cosmos, we are obsessed with this. We are obsessed with designing satellites, manufacturing them, and operating those satellites. So we make sure that each one of you actually can help solve those global challenges. We are talking about deforestation. We are talking about moving and logistics. We are talking about all the climate challenges that we have. None of those actually will be able to address unless each one of us can use these technologies as a tool for better. But you may be thinking, yes, but there are very big barriers that we have to encounter in order to be able actually to use the space technology. The first barrier that most people think about is, well, space technology is really hard, right? You have to be a rocket scientist or a space scientist in order to be able to know about that. You need to have things that work in vacuum and have things that are capable of working within radiation. And the answer is that yes, there is a requirement for all of that expertise, but many things actually tested properly and tested through the right processes can still be used. And when you follow a standardized process, you can streamline and reduce the risks on many of those technologies. Another thing that usually actually puts people a little bit off is that they think about all the bureaucracy, all the regulations, all the law, all the frequency filings and so on that they would need to be doing. And that usually means that it requires a lot of time and a lot of understanding on what's the law in each one of those regions. And that's another of the typical barriers that people encounter. And the last one that everyone knows about is that they usually feel that space is something really expensive, that only those that have a lot of money will be able actually to develop capabilities within space. But with the new space approach, these three barriers have, I wouldn't say disappeared, but have drastically been minimized and reduced. The technology, particularly once the CubeSat standard was defined, evolved really quickly in a modular way. And now you have a lot of all-the-shelf components and a lot of all-the-shelf capabilities that properly combined actually can lead towards putting a satellite that works in orbit. So you can rely on companies like ours, for instance, that build all of those capabilities, all of those technologies, and test them together for you. So you don't need to actually have all that knowledge that we were describing about space dynamics or space electronics. The other important thing that has happened is that speed has come to the space industry. And this is because companies in the rocket industry have started to have a lot more frequency launching. And as a result of that, everyone from a bureaucratic perspective, from an approval perspective, from every single area of the space industry has had to adapt to that faster pace. And this has now actually implied that a massive reduction in the time of the development of those missions. And if you combine both things, all of a sudden, you also reduce the price of those missions. So you go from traditional missions in geostationary orbit that would have cost hundreds of millions to now entire small satellite missions that can cost 1 million, 2 million, 3 million, depending on the sensors. So we have seen a 1 to 2 order of magnitude reduction in the cost and time that it requires to bring things to orbit. One of the things that I would like actually you to be very aware is that there are tools that actually enable the development of sensors and technologies that are fully compatible with standardized satellites. And again, at Open Cosmos, we are totally obsessed with that. We try to provide the software tools that enable people to design their own missions, to provide the development kits that will enable those sensors that you may develop at home or at your company or in your research labs to be fully compatible with satellites. So then once you have those ready, we can take care of the rest of the mission, put it in orbit, and deliver the meaningful data that you require. This team process is actually showing to be very, very, very effective. And the last thing that I wanted to share with you before I give the floor to the rest of the panel, it's a little bit of my journey as an entrepreneur in the space industry. I started selling what you see on the left. And for many of you in the maker community, you will realize that this is just a pack of a number of off-the-shelf components that you can find. There is an Arduino that I had that I had included with a small transceiver, and that actually it's called a CANSAT. It's one of the main boards of a CANSAT. A CANSAT is something that is used in the education community to teach students how to build something that resembles a satellite. Satellites inside a can, they call it. That's why they are called CANSATs. And the European Space Agency, NASA, and many others actually hold competitions for students that basically do different kind of missions that are launched in sounding rockets, not to space, but a bit high, and then they have to return to a particular target or perform different kind of scientific missions. That was the start of the journey of Open Cosmos. With a little contract that we got from the European Space Agency, we started generating the revenue actually that enabled us actually to dream a bit bigger. And believe it or not, 3 months after delivering that contract, we were already working on a satellite mission of our own. And that satellite, it's the one that you see on the right. This satellite was launched already 3 years ago. It was a mission that we delivered together with the founding team of Open Cosmos in about 6 months. And it's a testimony that with the right knowledge, with the right passion, and with a lot of working nights, you can actually develop technologies that fly in space, in this case, for an amazing scientific mission that monitored the ionosphere, right? From there, the journey has taken us to where we are now, where we are producing more than 8 satellites in our facilities in Oxford, with 50 people from over 17 countries working there together to make all of these capabilities and these technologies available to all of you. So that's all from my side. I'm looking forward to hear from the rest of the panel.
Thanks very much, Rafael. for this presentation. It was really, really interesting. And from Oxford, where you are based, we are going to travel to New York to meet our next speaker, David Colby-Reed, who is a research assistant at the Space-Enabled Research Group at the MIT Media Lab. His research focuses on designing participation, voice, and equity into the architectures of complex systems like law, economies, and technologies. The big idea is to design these systems that create patterns of social relations that are compatible with democracy. If we are in the future going to live in new cities on Mars or in the Moon, how will they be organized and ruled? Please, David, go ahead.
Thank you very much for the introduction and the opportunity to speak with everyone here today. I'm just fumbling with my slides for a moment. I'm sorry. No matter how many times we can do this in advance, it still manages to, let's see. Okay, I think we're looking at the wrong slide. I'll try one more time, and if I can't get this right, I will just forego the slides. But let's see. Okay, can anyone see the slides now? Is that working?
No, yes.
Ah, lovely. Okay, because otherwise I was going to have to do it without. But well, thank you very much for the introduction, and just so as to economize on time, I'll just get started. So. As Christina was saying, I work at the MIT Media Lab, where I am a researcher in the Space-Enabled Research Group. And the mission of the Space-Enabled Research Group is to advance justice in Earth's complex systems using designs enabled by space. And what that means, practically, is that there are projects like the Space Sustainability Rating. Rafael was speaking about the possibilities for constellations in low Earth orbit, for example. And so how do we manage traffic in that kind of setting? Or, other of my colleagues are working on different propellants for satellites, which can change the mission life cycles and mission design and business case for different types of satellite missions and remote sensing possibilities. And that, as Rafael was saying, can help enable more democratic access to space. I want to talk to you about some other more speculative and further future-oriented topics. And so, since we're short on time, I'll skip past that. I will say that the way I think about my work is that I work to build equity into the architectures of socio-technical systems, and we can unpack that some more in the discussion. But to give an example of some of the questions that I look at and some of the questions that I think the space industry needs to confront more directly, I want to open with an example of another technology that shaped the 20th century. So in order to make this research question make sense, just bear with me as I share two quick thought experiments with you. The first concerns how thoroughly technologies can change societies. So for this, I'm quoting now from what you see on the slide here is a quote from Samuel Schwartz writing a book, No One at the Wheel, where he discusses possibilities for managing fleets of autonomous vehicles. But he's trying to imagine what it was like before the mass adoption of the automobile and how, and as a way of thinking about how the automobile has restructured society. So if you'll forgive me reading the slide, as I travel back in my mind to New York City in the 1880s, I imagine myself talking to a pedestrian and explaining to him that within 20 years, we would shine a light in his face and he would stop, that he would hug buildings while he walked, and that he'd only cross at corners where the government said it was okay to proceed. If he failed to comply, he'd be charged with a criminal violation and be subject to arrest. The pedestrian from the 1880s would laugh at me and say that no sane society would allow that to happen. It was inconceivable. I would say that space technologies have the potential to be today's equivalent of the automobile. We're at a similar cusp of norm setting for new space technologies and business models. So here too, inconceivable impositions on personal freedoms will be proposed in the name of safety and profitable enterprise. Our challenge is to consider their implications for human life. So a second quick thought experiment. How do you quit your job when you work in space? This is a cocktail party version of the question, but just think about it. You can't just quit, if you're 9 months away from the Earth or what have you, if your company is providing your oxygen and radiation shielding and all the rest. How do you begin to manage the asymmetries of authority between, in this case, workers and a company that has space habitation, right? So I want to think about these further futures of space economies and space societies, because they can also help us think about questions on Earth. And so we can get to that bit later as well. What I'm going to do now is just briefly highlight a few points for consideration when we're talking about governance and social relations in space. And then I'll conclude by sketching some initial implications. So, there is no single space environment, but we can think about the features of the space environment as being, well, we can think about the space environment acknowledging that there are different planets and systems and so on, but it's lethal, it's vast, it's abundant with materials that can be processed as inputs to survival, transportation, and economic activity, but only with capital-intensive and algorithmically and robotically mediated technologies. So space is big. Sound will be heard via microphones and speakers and will thus be subject to always-on recording. Air pressure and content will be monitored and adjusted by artificially intelligent agents, which will monitor and steer human activity, attention, and emotional states. And radiation will be managed by routine structures and garments that will insulate humans from their external environments by controlling their movements. And gravity differentials will heavily influence the economics and potentially create natural monopolies and first mover advantages in space resource extraction and so on. So those are some features to consider when we're thinking about space. We also have to think about democratic or relational equality. Like, what are we working toward, and how do we conceive of equal or equitable social relations in a future space context? Where can we get some guidance for that? For that kind of guidance, I turn to a philosopher at the University of Michigan, Elizabeth Anderson, who writes about relational or democratic equality. And the big idea here is that democratic government is conditioned on the idea of relational equality, that each citizen is equal in stature, in rights and responsibilities, irrespective of whatever material differences exist between citizens. And we have like these axiomatic expressions of that. One person, one vote. Justice is blind. A jury of one's peers. These and other notions draw their meaning from relational equality. And relational equality is challenged by social inequalities on Earth, but those challenges are exacerbated in contexts beyond Earth. The lethality of space and extraterrestrial environments, and the scope and expense of the material inputs required to convert natural resources into human usable supplies, those are going to challenge relational equality. A third consideration here is that of private government. I was introduced to the term private government by Elizabeth Anderson as well, and she's written a book on it, but it's a term of art in a variety of fields, right? But you can think about private government as not necessarily a state. So government doesn't mean a state necessarily. It's just any kind of controlling system that has arbitrary, unaccountable power over those it governs. That's a private government. So on our present trajectory, future human habitations, occupations, and economies in space will be organized as private governments because the corporations that will finance these endeavors will determine the system of objectives, rules, and sanctions that govern them. The lethality of the space environment will restrict the exit options of those to whom these future governments are private, and will necessitate hierarchies of authority to produce just the basics of life. Anderson describes private government as a condition where you're subordinate to authorities who can order you around and sanction you for not complying. Well, that's going to be life on any space station. Just to survive, people have to order other people around. So what does that mean for human relations, right? Authoritarian social relations would appear to be the likeliest arrangement here because it's difficult for a free society of equals to take root in a context in which surveillance is total, government is private, and non-compliance with authorities is lethal. So what do we do with all this? How should we think about alternatives to our current trajectory? I'm working on research projects in a few domains, but I wanted to, and we can talk about them later, but I wanted to illustrate what I mean, and because it seems a little out there, this is speculative, right? But I think we can look to signals in the present that reveal some of our thinking about how to structure space societies, right? So I was looking at job postings because eventually when I finish this PhD, I'll want to work somewhere. And Blue Origin had this really cool looking job, right? The orbital habitat formulation lead. But you'll note that this job description doesn't consider governance and social relations and the implications there for living and working in space. And it doesn't anticipate the necessary governance skills in such a society. As you can see here, it's, we think about this in terms of business case and business needs and technology needs, but not the kinds of human relations and governance that will work with them. Another space company, SpaceX, Starlink terms of service. Starlink is a constellation of satellites for communications, for Earth-based communications now, but it's anticipated that Starlink will provide communications on Mars and between Earth and Mars as well. And over here, too, we see that SpaceX is envisioning Mars as a free planet and that no Earth-based government has authority or sovereignty over Martian activities. And so there's, again, this assumption that governance will happen at the level of the company. And I'm not trying to pick on Blue Origin or SpaceX by any means with this. It's just, I reference these examples to illustrate the lack of attention being paid to some of the governance challenges here. So I'm just about out of time, so I will just quickly restate the challenge. It's likely that governance regimes in space will converge on the operational and strategic management regimes of space companies. And so just as companies like Facebook today end up serving governance functions, the space companies of tomorrow will presumably serve a similar kind of function. And that leaves us with the design challenge. How might we design space habitation technologies and management systems that enable democratic equality among future spacefarers? So that's it for me for now. Thank you for that, and I look forward to discussing this stuff with you.
Thank you, David. Super interesting. I guess that in the part of the Q&A, we will debate a lot more about some of the things you've said. I keep one question in mind: who needs rules on the red planet? We will talk about it later. Thank you very much. So let's move on to our next speaker. I was going to say we will stay in Boston because I thought that David was in Boston, but he's not. He's now in New York, and I thought that our next speaker, one of the most marvelous and brilliant minds, she was in the MIT as well, but now she's moved to London. So, well, I'm talking about Mariona Badenas. She's really brilliant, as I was saying. She received a Bachelor of Science in Astrophysics from Yale University. She attended the Space Studies program in Israel and received a master's degree in astrophysics, cosmology, and high-energy physics from Universitat Autònoma de Barcelona and Institute of Space Studies of Catalonia. She is right now a PhD student in planetary science at the MIT, where she works with Professor Sarah Seeger and Julian Dewitt on stars and exoplanets. She collaborated with the Mars Desert Research Station, an international nonprofit organization operated by the Mars Society and dedicated to promoting space exploration and research on Mars. So, Mariona, please go ahead.
Thank you very much, Christina, for that introduction and your kind words. It's really a pleasure to be with all of you tonight. Let me share my screen. Okay. Hopefully you're all seeing my slides now. So yeah, good evening, everyone. As I said, I'm very happy to be here with you all discussing space exploration and space technologies and how they might benefit Earth. And as my title suggests, my talk today is going to be focused on Mars and on how we can explore the prospects of living and working in the red planet while staying on Earth and participating in what we call space analog missions. A space analog site is basically a place on Earth, remote and extreme, with environmental, chemical, and or biological traits that are similar to those of solar system bodies. And in particular, I will talk about the Mars Desert Research Station, or MDRS, which is a space analog site located in the western part of the US. And I had the privilege of going there in May 2018 as part of a crew. And here on the screen, you can see an overview picture of the Utah Desert, which is where the MDRS is found. And before I talk about my experience in the MDRS, I would like to step back and provide a little bit of big picture narrative behind my slides. And there are two aspects that I'd like to emphasize. First, I want to stress the importance of dreaming big, like my colleagues in this panel are doing in their respective professional ventures, because achievements such as, for example, landing on the moon or sending rovers to Mars would have never occurred if people hadn't dreamt big and hadn't thought about transforming humanity into a spacefaring civilization. And second, I would also like to emphasize the importance of connecting space and space exploration to everyday tangible things. And this is, I believe, one of the themes of this panel and something that also permeates my talk. So with this framework in mind, I'd like to start by inviting you all to travel back in time to the 1960s when the moon was a national priority for countries such as the US or the Soviet Union. In 1969, as many of you might know, the humanity landed a crew on the surface of the moon. And since then, apart from a total of 24 astronauts who have visited the lunar surface, we've never been back with other humans. In the early 2000s, NASA and other space agencies such as ESA or JAXA, so the European and the Japanese space agencies respectively, started investing more and more money into the possibility of going to Mars. And eventually Mars became the central goal in the space exploration plans of both national space agencies as well as private companies such as Elon Musk's SpaceX. And as you may know, Mars is the fourth planet in our solar system after Mercury, Venus, and the Earth. And it is at an average distance of 225 million kilometers from us, which is much greater than the distance between the Earth and the Moon. Therefore, traveling to Mars is inevitably going to be very challenging and difficult. On the one hand, from an economic perspective, traveling to Mars will require a substantial investment in order to develop the necessary technologies and equipment to send a crewed mission to the red planet. And then on the other hand, from a human point of view, astronauts will have to undergo very special training in order to endure a long duration mission of at least 6 to 9 months to go to Mars, plus the time on the Martian surface, plus the 6 to 9 months to come back. So overall, it's going to be a very difficult adventure, a very difficult project. But here's the question. To overcome these challenges and in preparation for a future mission to Mars, what if we brought Mars to the Earth? In other words, what if we went to a remote place in our planet, such as the Mars Desert Research Station, one with similarities with the Martian surface, and pretended to conduct a space mission in the most professional and accurate way, understanding, of course, all the limitations that result from the fact that we would be conducting this mission on the surface of our planet. And the answer to this is actually already being done in many terrestrial analog sites, such as the ones that you see on the screen. In my case, I had the opportunity and privilege to spend 2 weeks at the MDRS in the Utah Desert, which you can see in the top left corner of the screen. And I wasn't alone in this trip. On the contrary, I was part of a crew called LATAM 3. And this crew was composed of 7 people coming from 7 different countries, both from South America and Europe. In this crew, we had engineers, we had scientists, and we even had a journalist. And in part, the reason for having such a diverse crew is because all of us understood that a future mission to Mars with astronauts would, and an eventual settlement, human settlement on the Martian surface, would require and necessitate a very multidisciplinary crew. I guess this touches on what David was also talking about, the fact that we're going to need people from many different backgrounds working together as a group. And in my case, I was both the co-commander of the crew and the astrophysicist of the group. And so as a co-commander, I helped to prepare the mission and coordinate the research projects of each of the crew members, as well as prepare protocols of action to solve any problem that might arise during the mission. And as the astronomer of the group, I used 2 telescopes at the MDRS to study the sun, as well as to observe the night sky and study different objects. This is a picture of the Mars Desert Research Station, which, as Christina said, it's operated by the Mars Society, and it primarily has two goals. On the one hand, it seeks to facilitate the design, development, and testing of technologies that might be potentially relevant for a future human settlement on the Martian surface. And on the other hand, it also aims to promote space exploration, particularly of the red planet, and in so doing, inspire the younger generations and people who are studying in STEM-related fields, so basically science and technology. The MDRS is composed of 6 main structures, which you can see on the screen, and each of these structures is connected with each other through tunnels. There's a hub, which is a 2-story cylinder of 8 meters in diameter where the crew lives. Then the green hub, which is used for biological and agricultural experiments. The scientific dome for chemical, geological, and biological projects. 2 telescopes, as I said, to observe the sun and the night sky. And finally, a repair maintenance module, which is typically used to repair malfunctioning objects, including ATVs and Rangers, which are the vehicles that you see in the bottom right corner of the screen. And since I don't have much time left, and given that I've already presented a little bit how the MDRS looks like, I'd like to ask ourselves why a site like the MDRS, as well as other terrestrial analogs, are important for us today and for future space exploration. And there are multiple explanations there are multiple answers to that question. First, from a point of view of geomorphology, the Utah Desert is quite similar to the Martian terrain because it's located in this red rocky desert with quite a lot of dust, low humidity, and significant temperature variations, albeit less extreme than on Mars. From the perspective of research and strategies that we can test and implement, the MDRS provides an excellent opportunity to test technologies and equipment that astronauts might one day bring to Mars, as well as conduct experiments in a simulation environment. That also includes testing protocols for extravehicular activities, or EVAs, which are any walks that the analog astronauts perform outside of the main MDRS structures. A third reason why I think the MDRS is important is because it offers the chance to explore how microorganisms might live in an extreme environment such as that of a desert. And it also gives us the opportunity to see how plants might grow in an enclosed environment, which is something that might also have to be done on Mars, given the extremely high radiation that there would be outside. And finally, the MDRS is also a great place to see how the daily life of an astronaut would look like. It's a day during a mission, and astronauts in Mars would experience limited communications, as well as a limited food and water supply, which are things that we replicated in the MDRS. And then, during this stay in a terrestrial analog, we can also see how crews can try to develop a certain autonomy from the Earth, which is something that eventually will have to happen when we have human settlements on Mars. And I think I'm a bit tight on time, so I'll conclude my talk here. But I wanted to say thank you to those who are listening, and thank you to the organizers for having me today.
Thank you very much, Mariona. Super interesting talking. After in the discussion, I think we will have more time to deepen in some of the questions you've been mentioning. So from London to Barcelona, where our last two speakers are. First, we have Guillem Anglada, PhD in astronomy by Universitat de Barcelona, in the context of the Gaia ESA mission. After traveling the planet doing research in some prestigious centers in the USA, Germany, and the UK, he became a reader in astronomy at Queen Mary University of London until 2019. At that time, he came back to Catalonia as a researcher at the IEEC, the Institute of Space Studies of Catalonia. He is best known for his research on exoplanets, and he was the one leading the team that discovered Proxima b in 2016, the nearest exoplanet to the solar system. Also working on promoting the long-term development of a space economy, Guillem is the founder of the Sustainable Off-World Network. Guillem, please.
Okay, let me see if I can share. Hello? Yes.
Hello. Yeah.
You see a rocket? Yeah. Okay.
Yes,
okay. So let's see. So I'm going to tell you a bit why I'm talking today about developing a space economy, because as Christina said, I am a scientist, or I have a scientific background. I'm supposed to be using space or telescopes to look at stars, not planning to exploit the moon or dig holes on Mars. But I reached the conclusion after many years or things that we have been doing, and also the trend towards building bigger and bigger experiments and things we want to do in space, is that incremental growth is not leading us to something that it should be sustainable in the medium term, I would say. We are planning these new missions, which are going to cost billions. For example, we have the James Webb Space Telescope. It already costed 10 billions. And it's probably cost much more. And if we go to the next thing, even it's a slightly larger telescope, the costs are just ramping up at an incredible pace. This comes from the old ways to deal with space that has been mentioned by Rafa. But in a sense, if we want to make the next qualitative step, it's of at least my opinion or some other people also to address the question of why we are investing so much money in space, because money is resources. Money basically is work hours of people working on a thing. It's not just coins that you have in your pocket that give you value. It's workforce of people doing things. So why we want to put all these people to work in space if actually there is no return, or at least not immediate return or midterm return? We have to solve climate change and things like this. So going on this path and talking with a number of people, I also found that there is a lot of people outside space sciences that want to work on space. Let's say architects, engineers, sociologists, psychologists, biologists, things like this. They never have the opportunity because it seems like space is this very strange thing that you cannot do things if you are not a space scientist. It's not entirely true. And actually, there is a synergy of a number of things. So there are two essential technologies that need, or this is my distinction, people can argue about that, but two things that you need to really go to space and start, let's say, the new space era, not the space race, the era. So where humanity lives in space and uses it. One are the rockets, but they are already happening. And this is what's triggering now what's called the new space race. And there's another one that you will see at the end. I'm not going to spoil this at the beginning, but it's connected to many thinkers also of the 20th century. For example, one of my favorite physicists is John von Neumann, who invented or proposed quantum mechanics. He also had a theory, apart from game theory, that tried to think about some of these concepts of what a system would need to actually develop in a place by its own. And we'll go to that in a second. So, very simple, not very fancy slide, I know, but actually this is the most important thing why space race is happening now. It's because the launch costs have dropped dramatically. And you can argue why this happened. There are a number of reasons. The issue behind this, or one of the main issues, is actually because 20 years ago, the American administration decided to start a program to encourage small private companies. It's called the COTS, NASA program, to encourage small companies to actually develop space technology, giving the promise of a big chunk, big contract if they manage to deliver astronauts on the space station in 15 years, something like this. Anyway, several companies started to compete, and then, of course, SpaceX emerged among most of them, and actually they managed through a number of things, and subsidies actually is heavily subsidized, SpaceX. Now the launch cost has been reduced a lot, and of course this is putting pressure on all the other companies, therefore the prices are going down. As an example, Ariane 5, a gram of material brought into orbit by Ariane 5 costs $12. Why, if you use a Falcon 9 nowadays, it costs you $3. It's a factor of 4, which is a shame for Europe. That's another thing. There's a technological race here that's being completely lost by our continent. But then the Americans actually are on top of it. And then also, of course, now space, the big players are the US and China, without doubt. And you will see in a second why this is the case. I'm just taking now, for example, the moon as an example, what's going to happen in the next decade. The big geopolitical powers, essentially the US and China, are planning to set bases and do things on the moon. And this is just an example of what was the plan of the US 1 month ago. I don't know now, because now there is a change of administration, and we'll see what Biden wants to keep, because this plan was aimed at delivering astronauts at 2024, which was the last year of Trump's administration. So that seem to have changed. So we'll see how this is going on. But anyway, within this next decade, there is this plan of developing all these initial outposts on the moon. And the US maybe hasn't delivered cargos on the moon recently, but it's developing very serious launching capabilities through the private and also public sector. So US is running. The other one it's running is China. And I don't even need to talk about plans. They landed a polar rover this year, and 2 days ago they landed on the moon, and yesterday they lifted off from the moon, and they are making the first sample return in 30 years. So clearly the race is on. So what Europe is doing, well, Europe is planning in 10 years maybe be the track delivering cargo to the space stations, but there's no serious thing going on like developing really heavy rockets and planning infrastructures on the moon. That's a big political thing that can be discussed another day. But in any case, there is this space race. You can see clearly these two powers. There are other smaller ones that are more or less aligned with these powers in different versions. Can be Emirates, can be Israel even, small countries, can be Brazil, India are also playing their game, and small companies popping out and trying to go into the market. Okay, this is happening. This is good, but this is kind of the first technology. This is enabled by these rockets that we can transport things and put them in the moon. And then we need the second thing. And for this, we've been working with people that are not space scientists. We competed actually in a competition for the Mars Society to try to think what the city on Mars would need to develop itself. That was not a requirement of the competition, but we actually tried to make the exercise. So let's see. And it would take me 2 hours to explain everything at a very high level. But anyway, the main message is apart from the rockets, what you need is when you are on Mars, you need to build an amount of infrastructure and a number of machines to actually incorporate this person into the city. And if you want to do that, let me skip this. You have to use a number of design principles that are very different from what we are used to do on Earth. Actually, we should be doing this on Earth, but we are not doing it. So if we are planning to grow a city or grow a village, we should incorporate self-sustainability of growth, and also not only growth, but also maintenance. It has to be at design level. It's not, oh, let's see what we do later, we will repair the house. There has to be resilience as well in the design, because Mars is a remote location, but also on Earth. You need a power system, a power grid that doesn't fail because one power plant just collapses. And also, actually, it has to be an exciting place to live. You cannot just send people there and be sad. You have to provide incentives of a welfare state, a place where it's big enough that you can change locations. It's not that you are trapped into a cave and live there. So when you put all these constraints together and try to make the exercise, just trying to be very, very earthbound in a sense that we want to really build it, is not science fiction, it's extrapolation. You can make an inventory of everything that you have to collect, all the machines you need, and so on. Very long exercise, doesn't matter. And then you end up with a very long list of things that you need to build. And from this list, you can transform or estimate what materials you would need from Mars. Mars has very different resources from Earth. You need to take the air from the CO2 of the atmosphere. You need to collect the water from the underground, etc. You have to replace materials. But this, you can see, if you see this list, this is nothing really science fiction. Instead of using concrete, we will use sintered regolith, which is taking rock and pressing it and converting it into a block that then can be used for construction, etc. So if you do this exercise, you spend a lot of time and you read these numbers, they are order of magnitude, can be off by a factor of 2 or 3, but it gives you a sense of what actually would take to add one person on a city on Mars. And we are talking, for example, about 1,300 tons of material. Most of this material is actually concrete and things that you need to make buildings. And you might think that this sounds like a crazy number, 1,300 tons, but actually on Earth, it's estimated that each person in a developed country consumes about 700 to 1,000 tons of material from your environment. So just for you to be alive and to be in your city, over your life, you'll be consuming a similar amount of materials. The other thing that you need a lot on Mars is collect a lot of water. Actually, it's not for drinking. This water is needed to make organic materials, to make, for example, things like plastics, because on Mars you don't have oil. Therefore, if you want to make organic materials, you need to get the carbon from the hydrogen from the water. And then CO2 as well, because you need the carbon. Actually, oxygen is not a problem. Actually, oxygen, every process you do on Mars to extract any material will produce tons of oxygen that you don't need. And a very important number, and related to what David was mentioning before, when you estimate everything that you need to grow this city, you need a huge amount of power. You need around 100 kilowatts of power. This number might not tell you anything, but just for you to have a reference, in a developed country, a person typically consumes continuously 10 kilowatts of power. So that's a factor of 10. Or your home, when the people is there, it's consuming about 3-4 kilowatts of power. So to keep a city functioning on Mars, we need about 10 times more power, which means actually that each person should be also doing kind of 10 times the work. So per person, the productivity of the person should be 10 times higher. This requires artificial intelligence and so on and so on. So bottom line is that, yeah, we need the rockets, but we need something also different, which is the challenge that I launched to the Make FAIRE assistants, because this is about making things. So if you can make a self-replicating machine that can be able to replicate itself using only local resources, you will have solved the other problem that we need to actually start the space era. That's not solved. And that doesn't need to go to Mars to be solved. You can do it in your garage, because it's about taking sand and extracting silicon, and from that make pipes and make devices that eventually you make a system complex enough that it's able to make itself, like with a 3D printer or some philosophy like that. And that's all I wanted to say. Thank you.
Okay, thank you very much, Guillem. And now we are going to talk to the last brilliant mind of this evening. He's also in Barcelona. We are talking about Ignacio Rivas. He's the director of the Institute of Space Studies of Catalonia, the IEEC. He's also a professor at the Institute of Space Sciences, and he holds a degree and a PhD in physics from the University of Barcelona, and carried a postdoctoral stay at Villanova University in the USA with a Fulbright scholarship. Rivas' work primarily focuses on exoplanet discovery and characterization. He actively participates on ground and space-based instrumentation projects to discover new planets similar to our Earth for the eventual search of life. He holds high-level responsibilities in several space missions and astronomical instruments, and he's also deeply involved in the development of nanosatellite projects as part of his role as director of the IEEC. Dr. Rivas has published over 200 research papers in international journals, including Nature and Science, and he is strongly committed to outreach activities and dissemination of scientific results. Please, Ignacio, go ahead.
Thank you, Cristina. It's a pleasure to be here. Hi, everyone, and to share this evening with everyone, with you guys. It's such a distinguished panel. I'll present some slides here, and I'd like to go back from Mars and from the Moon and talk a little bit about some of our everyday problems down here on Earth. And I'd like to address how space research can help us with addressing those kind of challenges that we have down here. So let me just start by saying that okay, I'm going to be talking about a lot about applied space research, but I also want to really highlight the value of basic research here as well. And you know that we are building powerful telescopes on Earth, and also very big space missions that we're launching with space agencies. And that we're using all these machines and spacecraft to really unravel the mysteries of the universe, right? And you can see very nice pictures here on the right. But it's not only that. This is the first link of a value chain that also leads to technology development and eventually also to society advancement. And you can see here that that development leads to techniques and technologies that can be applied then to everyday life. And now, besides this basic research, okay, we all know that, and this has been mentioned by a number of people before, by Rafael, for example, on the UN Sustainable Development Goals, and there's a list of goals that we have to try and find solutions for, and the challenge is doing this before 2030, right? So, and I'd like to discuss how some specific examples of how these goals can be addressed from space. And I'm sure you know that already that many of these can be tackled with space missions, but maybe you'll find some surprises here as well. So there's two big topics that I'd like to address. One is Earth observation, and the other one is telecommunications, where space missions do make a big difference. And the fact that observing Earth from space is of big value has been recognized for a long time, actually. And there's big space programs like European Space Agency's Climate for Space Initiative, or also the European Copernicus program, or Europe's Eyes on the Earth, that provides data actually for free for many applications to try and understand the Earth, our own system. But as Rafael was mentioning at the very beginning, there's also an impending revolution here, because very small missions like nanosatellites are making a big step forward, also big entrance here, because they allow us to get information on the Earth for a relatively low price, and then make it accessible to many different actors and many different companies interested, for example, and also opening a market here. And there is a big area of Earth observation using CubeSats. There's many ways to observe the Earth, both in microwaves and also the optical and other wavelengths as well, of course. And for now, just because of size and because of power limitations, most CubeSats use passive detectors. Passive meaning that they just observe whatever is coming out of the Earth or whatever the Earth is reflecting. And from that, there's powerful imagery and data collection. And sometimes even these nanosatellite missions, these CubeSats, use what's called signals of opportunity from other satellites. They're also transmitting signals that then can be picked up by these nanosatellites and used to obtain information from the Earth. So there's a huge range of applications to this new era of using very small satellites, very flexible in a way to gain information on our own planet. I'm going to show you a few examples here. And it goes from see, there's a number of sustainable development goals that are addressed here. For example, one can obtain, by using satellite data, information on crop conditions in some areas actually on all the planet, and then potentially understand whether crops are going to be bad or good on some specific year, for example, and then plan measures ahead of time before famine strikes, or measuring soil moisture, and then also the health of crops and forests and woods and so on, or measuring the salinity of the ocean, and then understand currents and events like El Nino or La Nina, for example, or address the risk of wildfires, and then be able to implement measures before that those wildfires strike. Or even like today, we're talking about epidemics all the time, and even from space, one can actually monitor how likely it is that some epidemic spread, and how likely it is that it's going to be a bad or good year for some seasonal epidemics, for example. So all this comes from space-based data, partly, of course. There's also data from other sources as well. And these are products that are made by combining data that comes from missions. And especially, there's an area where small missions can have their say. The other one is telecommunications. And we all hear about 5G and Internet of Things and so on. And here also satellites will play a huge role. And there's many of these network designs that are relying on satellite missions, and this deployment of lots of satellites that will be available at any point in time will make it possible for anything that we can think of have an internet connection that we can remotely monitor and probably and potentially get data on, and therefore act if anything is not going as expected. So these are all revolutions that are taking shape, and it's not going to be long until we see a lot of these actually happening. Probably just a few years, if not even less. And even the technologies in terms of cryptography and secure communications will probably rely on satellite links, because otherwise keys cannot be kept to a sufficiently high level of security. And as Guillem was mentioning, and Mariona as well, we can learn a great deal from closed systems, like bases on the moon or Mars, and some of research that is being done today, like the Melissa pilot plant at the Autonomous University of Barcelona. And there, this is teaching us how to make more, let's say, sustainable use of our resources. And that kind of teachings also can be applied to our own planet, and then try and be a bit more respectful and less and consume less resources to make it last a little bit longer. So in my last couple of minutes, I'd like to also come a bit closer. I understand that a big fraction of the audience may be from the Catalan area. So you must know as well that there's a lot of activity, mostly in the in the nanosatellites domain, and in what we call new space. And there's programs that are now being developed, and there's a few satellites that have been launched from here, actually, or I mean, built and launched from elsewhere, but built from here. And using, for example, the CubeCat program that's mostly pushed by UPC, or programs to develop techniques to use these like signals from other satellites to probe our own atmosphere. Developments to get more payloads actually for these small satellites, using enhancing, for example, a global navigation system, satellite systems, or even facilities that exist here in the Catalan area, like the Astronomical Observatory of the Montsec or the Nanosat Lab, for example. And I'm just finishing by saying that there's only a few weeks ago, there was a presentation of the new space strategy of Catalonia. And as you can see here on the right-hand side, there's a lot of already companies and institutions involved in the new space domain here in our neighborhood. And there's actually 2 upcoming missions that Catalonia will launch in the next couple of years, a year and a half. And that's one Earth observation mission and another telecommunications missions for 5G and IoT. That will put these technologies to a test. These will be pilot missions that we hope that in not too far future we will service from, and they will all get information from. So this was my tour around the Sustainable Development Goals and how space can help to address them, and in particular this new space revolution that will probably change our lives in the coming years. So I'll stop here. Thank you.
Well, thank you very much, Ignacio. Super interesting. Now, if you want, we can start like the Q&A section. We can discuss a lot of the things you have been mentioning during your talks. First of all, we were talking about the moon, about Mars, but my first question would be, are we going back to the moon? Are we going to go to Mars only because of science? What do you think?
I don't think so.
No?
It's not. It's too expensive. It's just too expensive. Unfortunately, we have said all the good things or good reasons why we are going to the moon, but it's happening now because of geopolitics more than anything else. We have to take the positive side of this. Competition in a healthy way. It's better to go to the moon and compete, putting large rockets and things on the moon than launching rockets to each other. So I think that, in a sense, it's not as bad as it might look like. But anyway, as David was saying, these kind of things, this behavior leads to consequences a bit further out in the way. So I think it's not going to be science. Science should be there. It has to be the driver. But also, we don't want to be pointed out and say, you are spending billions on your telescope on the moon. Yeah, come on. This is not what we are doing. Anyway.
Yeah, I don't think even science was the driver in the first race to the moon, actually, right? So I don't think it's going to be the driver in this one either. It's probably going to be an economical driver, and of course, now it's geopolitical. But when the race is not over, but getting to the moon becomes more feasible, then it's going to be also an economic use of space, right? And there's plenty of resources. There's companies thinking about how to exploit them. A lot of ethical questions, as it was also being pointed out. But yeah, science, sadly, will probably not be the thrust for this, for long at least.
What do you mean by geopolitical?
You want to plant your flag somewhere and claim that you made it first, right? And it's not really yours, but if you're there, maybe you can make good use of that, right? I would think that this is what geopolitics means here.
Mm-hmm.
I guess
I might also. Oh, I'm sorry.
Oh, sorry, David. Oh, okay. I was just going to add that maybe I'm a little bit naive, but of course, there's always going to be a geopolitical reason, and there's always going to be a scientific drive, which might be fueled by by those geopolitics involved. But at the same time, I feel like if we compare today to the 1960s, to the 1970s, and even to the 1990s when the ISS was being built, we see a shift towards more international cooperation. And an example of this is the recent Artemis Accords that were proposed by NASA. As these are accords to perform space exploration, I guess particularly on the moon, but it probably also applies to other bodies in the solar system. And the exploration that it envisions is one that is rooted in the values of international cooperation. And these accords are signed not by space agencies, but by actual countries. So that's also something very interesting, which again points towards this cooperation between the private and the space and the private sector and then national space agencies. And it's not so much about space agencies, it's about countries going together to the moon and beyond. So yeah, maybe I'm too naive, but I think that there's really a change in the way people are seeing space and cooperation in space.
Mm-hmm. David, I think
on the heels of your optimistic take there, maybe I'll offer, this isn't pessimistic, but it is just like a point of concern or consideration. And there are trade-offs too in any sort of policy regime or planning regime, like between science activities, commercial activities, national security ones as well, and so, for example, there are companies that are planning missions to mine asteroids for, organics that can be used for fuel or radiation shielding or what have you. And, in a situation like that, how do we weigh the economic value of mined materials, whether it's something like, water ice or platinum or whatever it is from asteroids, against the scientific or research value of being able to see something that is unspoiled and, a better, that helps answer questions about how the solar system was formed and so on. And so there are going to be trade-offs between those agendas. And, I would be curious if, for any other panelists to correct me on this, but I feel like there's not broad consensus on how those trade-offs should be made and how consequently we should represent things like property interests in mined materials, and so there's some interesting tensions there that are probably going to be resolved quickly because people are planning these missions already, and so there will be a need to make rules soon.
Do you think that maybe we should protect the space and the planet and everything like we protect the Antarctica? We can go there, we can. You say no, Guillem?
Maybe the sea is operated, but you cannot just block space as the Antarctic continent, because that would also include the low Earth orbit and all the services. And also the private company is not the evil. Also be careful, because we are thinking always in the private company is a group of individuals that organize themselves to make something, to make some money, yes, but also because they have a plan, because they like surveying oceans with satellites. So it's a good thing as well, a company. And it's representative of the people trying to do things on space. So we cannot just block ourselves doing that. But yeah, some regulation should be there. And the regulation we have now is 30 years old. So yeah, I mean, it's kind of very obvious that needs to be updated. We should do it, but it was mentioned the treaty. Mariona said ISA didn't sign, or many of the European countries didn't sign the space resource agreement that NASA issued, for example, or NASA or the US started. So there were very obvious missing partners in that attempt to do international cooperation, for example.
We are talking about companies. Most of you in your talks, you were talking about people developing that now technologies are cheaper and that you can develop technology at home that you can then put into space. For example, we have these experiences of a lot of students in the university or even in high school that they are like making these cube satellites or nanosatellites, and they can be in the space. So is this also regulated? Because I was thinking about, Ignacio was talking about the 5G, and I was like thinking about all these satellites like going around the Earth. So I don't know whether it's going to be space, for all of us, or they are going to become more space debris in a way. So is there any regulation going on to regulate all this?
There are regulations a lot, and there are regulations also in the making. And I think that it's very important that we put the right regulations to make sure that we keep the space environment sustainable, and that we make sure that companies and organizations of all kinds can use that environment safely for themselves and for others, so we can keep actually bringing the good things that technology enables. Mariona has mentioned international collaboration, and I agree that if there is one industry, one area that can catalyze international collaboration, or that could catalyze that international collaboration, it's the space industry, because it looks at two things that could unite all of us. One is exploration and looking at new things. This is something that we all share as human beings, right? And the other thing, it's taking care of our planet and taking care of all the key challenges that we have down here on Earth, particularly climate change. And none of that is going to be possible unless we have these technologies providing the right data, the right information, and the right services to be able to do all of that. So I think there's never been a more exciting time actually to be an entrepreneur in an industry than right now in the space industry, because you can look at the downstream applications that come from that data and try to solve problems that you really, really care about. Or you can actually look at developing new sensors, new technologies, new capabilities that can be put into orbit as new infrastructure, deployed really quickly and affordably to actually bring new data that can serve further those purposes. So I would encourage everyone to give it a try.
Okay, Rafael, you were talking about regulations. Who is regulating, or who should regulate this space use?
There are all the international bodies. Like, I'm not an expert in law, I'm an engineer. but of course, for instance, in terms of frequency allocation, there is the ITU, the International Telecommunications Unit, I think it's called, which basically regulates how the spectrum is used, both for terrestrial applications and for satellite applications as well, right? That's a body that regulates the use of that particular thing. Then there are national laws. And international agreements that rule broadly on how the use of space should be, right? In the UK, where we are, they have a lot of lawyers. So they pay a lot of attention actually to the regulations, the contribution towards the regulations, and particularly the topic that you have mentioned, Christina, which is sustainability of the space environment and space debris.
Okay. We were talking also about funding, about huge amounts of money, that this is changing. I mean, sending a mission to the moon back in the 60s, it was really super expensive. Now, more and more, these technologies are a little bit cheaper, and private companies are making this even cheaper. But this is something that I don't know if it's something only because of the COVID thing, but people are more and more like saying, okay, why are we going to invest so much money, so huge amounts of money in this new mission of the, I don't know, for example, this week, the ESA presented a new mission to collect these space debris we were talking right now, and to clear a little bit this orbit we need to use very much to deploy all these technologies we are talking about. And people were saying, okay, but why should we invest so much money in this mission and not in COVID? And I think Ignacy would like to answer that.
Yeah, I can address. I get this question quite often, actually, and yeah, I think I think it's, you said it yourself. It's not about putting money on space missions or something and not on something else. It's about doing everything. And I think that we have to, as a species, as humans, we have to be able to satisfy our curiosity, our need to learn and to explore. And that is just curiosity-driven research or basic research. And that kind of curiosity has been with us for since dawn of time, right? So humans are curious, and we need to be the same way, in a sense. And that basic research, let's say, pools in a way technology development and technology advancement, and that technology again pools societal advancement. I mean, usually for the better, and we keep growing in this way. So it's not that we have to turn all our put our money, all our money, collective money, into sending missions to space. Just that we have to be able to afford a small fraction of our resources to keep exploring in a way. And at the same time, we have to keep coping with with improving our everyday life. And I showed a few examples that you can make both ideas coexist by having space missions that will help us with our everyday life. But I think it's funny that it's usually questioned whether we should be sending money to space. And I don't remember who said it, but it's not about putting lots of coins and stuff. I think it was Rafael, and sending them up to space. It's about training people. And actually Guillem said that as well. It's highly trained people that put their minds into doing something phenomenal, right? And it's not like, that's not a money waste. It's just a money investment. And from that comes a lot of other good things, I would think. So I could extend this for a lot longer. I hope I made my point that we have to be able to do both taking care of ourselves and our planet, and also sort of free our imagination and our need for exploration.
I would add to that.
Actually, oh, please.
Oh, yeah, sorry, go ahead, David.
Well, thank you. But I was just going to amplify your point, Ignacy. I think, like, I suspect, Rafael, you were about to do the same as well. But like, these can be investments as well. And Ignacy had the slide showing the Sustainable Development Goals up, for example. And space technologies are great for like dealing with challenges that we face right now. I mean, especially in a time of like climate change and global warming. I mean, better predictive capabilities for storms, or like satellite-based communications, to provide redundant communication systems in the event of natural disasters. I mean, these things are investments, just as there are investments in human capital as well. And because I'm in the US, I'll put in a quick plug for modern monetary theory. But like in the US right now, I mean, like the cost of borrowing for the federal government is negative. Like people will lose money on inflation protected bonds for 10 years. I mean, so like this is a brilliant time to spend money on useful infrastructure and human capital, I think. So I don't see there being as stark a trade-off as that question sometimes assumes, and I know on this panel we're like airing the idea, but I wanted to put that out there as well.
What I was going to add earlier is that I really believe that only what is properly measured can be improved, and there is no better way to measure things globally and to understand how things work globally than actually deploying satellites and space infrastructure. That's why it's so critical, because without those measurements, we don't know if it's going to rain tomorrow. We don't know how climate is going to evolve. We don't know how we are using natural resources. And if some of our actions are having very noisy consequences to the environment, to our own lives, to our health, all of those topics are not disconnected. And I think that the space technology should start to be seen as a key enabling tool to solve all of these problems. It's just that, just like a computer helps us communicate better, right?
Because Rafael, all this data that all these satellites are gathering, that in theory is improving our everyday life, are these data public? All this data is public, because you were talking in your talk about democratizing technology.
A lot of it is. There are a lot of investments, particularly in Europe, actually, in putting satellites that offer that data for free to everyone, not only to scientists, not only to governments, to everyone. And then there are obviously additional infrastructure, additional satellites, additional constellations for more specific data sets or complementary data sets that actually are driven by private companies. Mm-hmm. And those private companies actually receive investment from private entities and from public entities actually to deploy that infrastructure and be able to provide more diverse, better data that enables actually to solve a lot more problems and build more business propositions that can also improve that economic cycle.
Okay. Going back to Mars and going back to the moon, there was some ideas. There were some ideas really interesting. Sorry, about, for example, how I'm going to retake the question that was posing before, David. How should we rule these new villages that these new cities we are going to create on these planets? Are we going to apply the same relations that apply on Earth? Are we going to rule with the same laws that we have here on Earth? Is anyone thinking about all these things? Because it seems that it's going to be our next future. So I don't know, David, if you want to go on.
Well, I mean, I'll venture like a provisional answer, but I'd really love to hear from other folks about this too. I mean, because I think, we've referenced existing law, right? I mean, the Outer Space Treaty and implementing legislation at various national levels across the world for spacefaring countries, provides that you're responsible for the country from which a launch takes place, is responsible for the thing. So if SpaceX launches from Texas, like the U.S. is responsible for what happens with the satellites that's deployed, and if making sure rocket components are if they injure someone or some other asset in space, there's liability for that, right? I think that kind of national regime will be challenged as we see more space operators. I'm thinking over the next several decades, so not tomorrow, but over the next several decades, I think it'll be harder because you'll see more and more stuff happening in space as well. There'll be more space-based assembly and more, asteroid mining operations if they're running for years or something. At what point do you start to cut the tether between the site of the launch and work, or something that happens years later, right? And so in those cases, I think we're going to start seeing systems of law and develop, just to provide how do you ensure an orbital space station that is assembled with components that are launched over the course of years from multiple sites, right? If it's a private concern, I think we're going to start seeing more space law that is new and not. I don't know. I mean, there are different approaches. You could see. And with the U.S. in 2015, we passed the Space Resource Utilization Act, which provides for private ownership of mined materials from asteroids and other celestial bodies. That has spurred a series of changes in national legislation in, Russia, the UAE, Luxembourg, all these other countries are now passing similar kinds of legislation to allow for private ownership of mined resources. And so I think you'll start to see, one country set an example and then it becomes a global standard, much in the way that I don't know. I mean, I don't know the history very well here, but I'd be very interested in seeing a good history of this. But how did modern accounting standards take root or across the world, right? Before matriculating at MIT, I ran a small business, and we were organized as an LLC in New York State in the US, and we could do business internationally because our legal designation was acknowledged. You know, like we could do like financial transactions because there was a standardization of accounting and, you know, money laundering rules and all the other stuff to enable that. And so I think we'll start seeing more systems emerge like this. I think the questions that, you know, I think about often concern, well, you know, what will that mean for human relations? I mean, will we see like major monopoly kinds of players? Because I alluded to this in the remarks earlier, but there's a major cost advantage if you're a first mover, for example. If you can have a base on the moon or from some other celestial body, your launch costs are a lot lower. And, you know, as Kim was saying, like that's a major driver of any kind of, economic argument here. And so how do we think about competition policy when there are these, I guess you could call them network effects of first mover advantage? Or how do we think about, obligations to one another? Like with the law of the sea, if there's a stranded vessel, you know, like a ship has an obligation to rescue the people stranded. Like there are all these areas that bear on how we relate to each other as humans and what kinds of relations humans have to institutions and to one another. And so it's a rich area of exploration. I'm sorry, that's a poor note on which to end this remark, but anyone else want to pick up on that? Because there's so much there, you know, that I think is very interesting.
I think something that I might add to what you said, David, is related to the question of who is going to go to Mars when it's time for us to send humans to the surface of the red planet. And the reality is, and I was the naive optimist earlier, and I guess this is my pessimist side. The reality is that only about 500 people have traveled to space. And of those 500, if I may add, only about 10% have been women. So there's a big gender disparity in among astronauts and also in the space sector, unfortunately, both at the industry level and also at the academic level. That being said, it's clear that space is dangerous, and it's also a luxury only for a very limited part of the population, and our planet is very big. So who is going to make that selection? Who is going to go? Who is going to be selected to be part of the first human settlements? Those are questions that I want to throw out to the audience. And I guess bringing it a little bit closer to Earth, I remember back in 2016 at the International Astronautical Congress in Mexico, in Guadalajara, Elon Musk was giving a talk about his plans to explore Mars and send a crewed vehicle to Mars. And one of the last questions that he received was a question from what I think was an Eastern European woman who had dreamed of working for the American space sector because as it is a fact that the US is one of the most important powers in the exploration of our solar system. And her question was, I want to work for SpaceX. I want to contribute to sending humans to Mars, but I cannot even work for this company because I'm not American. And she finished with a question that has stayed with me since. She said, "You're trying to become interplanetary, an interplanetary species, but when are you going to be? You're hoping for humanity to become an interplanetary species, but when are you going to make your company international and a company that also accepts people from other places?" And so these are just some thoughts that I want to throw out for some food for thought. It's not as when building communities on Mars, we're going to have to think about many different aspects, from how to rule those societies in the red planet to who is going to go there and become part of the first human settlement.
Mm-hmm. This is something that I was thinking about when you were talking about. You were talking about sustainability. You were talking about growing new economies. But here on Earth, we have not managed to solve all these problems. We are not very sustainable. We have this climate change thing going on because because of all the things we have been doing to the planet. We are not fair in terms of what you were talking about, Mariona, of gender balance and everything. So what makes you think that we are going to do it like better when we are on Mars or on the moon?
Because there's no choice. And that's a big driver, actually. So on Earth, you say, oh, I want to build a sustainable house. It will have awesome solar panels. They all come from China. And they will have all these high-tech things on the house with these very efficient heating or things or foams that are made in Latin America. And it looks, oh, I have a house that doesn't consume anything, but the footprint that left that on the planet are your electric car with the lithium batteries. That's terrible. That's terrible. And we can't allow this because on Earth, it looks like it's coming for free. The air is for free. The water is for free. You don't have that luxury when you operate a wall. I mean, if you have a rocket, you can send a rocket every week, which costs you $1 billion, fine. But this is not going to happen. So when you are forced to make a design like this, then by design, you have to put all these things that the economy has to be closed. The economic circles, the materials have to be closed. We have to learn how to live in this closed environment, to relate with each other because we depend on survival. It has to be by design. And actually, Ignacy pointed it out. It showed in one slide. All this closed concept of economy, we have to train it somehow. And we haven't managed to do it in 2,000 years on Earth. A space gives us we could do it without space, but actually it's probably going to need space and going to the moon and trying to survive there to actually try to work these things out properly, because we are not capable of going out of the box on these things. It's offering an opportunity in this sense. It doesn't need to be space. It could be the bottom of the ocean. It's the same problem. So maybe it's on the bottom of the ocean that we do it. But putting ourselves in these extremes is how we then learn and really realize how many tons of crap we have to use to just put a person on a city, or even the amount of surface of land that we are using on Earth for agriculture is crazy. It's crazy. But when you do this from space, then you realize the numbers come crystal clear, because there's no way around this. You cannot depend on some tropical island producing oxygen with the plants, these kind of things. Yeah.
It's funny, but I agree that space has helped already many times actually to change perspective of people down here on Earth. And astronauts actually talk a lot about one thing that is called the overview effect, which is the impression that they get of seeing the whole Earth as one. Once they have seen it from up there, there are no frontier, there are no borders. They see the same problems in one side of the Earth that they see at the other. And that new perspective actually has empowered a lot of action from them, inspiring a lot of people down on Earth actually to solve some of these problems. And they tend to say that if people governing the world, active in governments, were sent to space to see it from that perspective, potentially some of the geostrategic and geopolitical situations that we are facing could be solved from that new perspective.
Well, maybe just chime in to note. Oh, sorry. After.
Yeah. Okay. No, just a very short note saying that I don't think humanity's track record is very good in this respect so far. So I'm just hoping, and coming back to Christina's question on regulations and how we will do this in the next step, that we do better than we've been doing so far, right? And then and Mariona's point about becoming global and becoming international and becoming mankind, let's see, exploring space and making the next step forward, and not specific countries and nations doing it. I think that's already a big thing. I have to say that I'm optimistic in nature, but not exactly optimistic in this respect. So I hope to see some evolution in the coming years towards this direction, because we're going to be forced to, as Guillem was saying. Well, we have to build somehow a better and sustainable world. So maybe space will teach us to do that, and maybe we'll learn the hard way. Hopefully not, and hopefully we can turn things back, and space will teach us a few lessons here. So the next decades will be key here, I guess.
David, did you want to add anything?
Just a quick note. I mean, like to be optimistic for a sec, like like the rest of the esteemed panelists. I mean, I feel like Rafael, you mentioned the overview effect. We're actually working on a study now, a psychology study and organizational behavior study that simulates the overview effect in virtual reality. And we want to see how that changes, whether, and if so, how it changes behaviors in a negotiation and cooperation task. Like we can design different kinds of institutions in space-based applications if we have to use the constraints of like closed material ecosystems or closed economies, and we are relying on the different types of psychological outlooks that are occasioned by the space environment. You can think about institution design differently as well. So like there is a lot of encouraging stuff there as well. Like as a design challenge, moving to the space context can help us think about these human relation questions on Earth better too.
Okay, so let's hope that space technology, space exploration will lead to a better future here on Earth. We have to finish this super interesting debate because we are running out of time. In fact, we are like 5-10 minutes late. So thank you very much to our 5 super brilliant speakers. It's been super interesting. And well, I hope that the audience has also found interesting our panel today. Thank you very much.
Thanks to the moderator.
Thank you all.
Good job.
It was a pleasure speaking with you guys.
Next time in person.
Visiting Spaces, Maker Faire Girona. Sabéis, en este bloque visitamos lugares interesantes, lugares donde la tecnología tiene un papel relevante, pero también donde tiene un uso interesante, un uso que a veces sorprendente, a veces maravilloso y muchas veces único. Y en este caso tenemos una oportunidad única de hacer una visita que la verdad es que va a ser espectacular al Supercomputing Center, y nos acompaña hoy Oriol Riu, Site Manager de Centro Nacional de Supercomputación. ¿Qué tal, Oriol?
Hola, buenas noches. Aquí estamos.
Pues nada, encantado de tener la suerte de poder visitar de primera mano BSC, y nada, creo que tenéis todo tipo de cosas para enseñarnos, así que cuando quieras puedes compartir pantalla y empezamos esta visita tan interesante.
¿No está compartida ya? Compartir ahí.
Ahí vamos.
Ok. ¿La tenemos ahí?
Vamos a ver que nos confirmen un momento. A ver si se ve.
¿Sí?
Creo que sí. Vamos a ver si nos confirma. Tenemos a la nave nodriza que despega. Dice la nave nodriza que no se ve la pantalla. Vamos a ver qué ocurre. Mientras conectamos, simplemente recordaros que estamos ahora mismo en YouTube. Sé que veo por aquí que hay gente conectada. Vamos a ver las tripas, nunca mejor dicho, de este supercomputador. Justo ahora estamos viendo ya la pantalla compartida. Va a arrancar la presentación. Cualquier duda que tengáis nos la podéis dejar en comentarios, y cuando acabemos esta visita lo veremos. Y aquí empezamos con esa visita ya que se ve espectacular desde aquí. Oriol, todo tuyo.
Millor, merci. Bona nit, nois. Soc l'Oriol, sí, el que deia el César. La idea és fer-vos una presentació en dos parts. Una primera part són unes quantes slides per ensenyar-vos el que és el centre, el que és la màquina i també el que és la nostra recerca. I una segona part que seria ensenyar-vos una eina virtual perquè vosaltres, quan vulgueu, podeu fer un tour a el que és el nostre site, d'acord? Bé, de fet, el que és la màquina es diu Mare Nostrum. La màquina en si és la part central, aquestes tres files. Nosaltres dividim la màquina en tres parts. La primera fila, això l'ample que veieu amb tot de llumetes de color verd, això és el disc. Aquí actualment tenim 14 petabytes de disc. Des de fa unes setmanes tenim ja externament un robot de 160 petabytes, que és ja preparat, ja el comentarem després, per la nova versió de Mare Nostrum que està al Caire. Què més? Això és disc, és molt, però no és la prioritat d'aquest tipus de màquines. La prioritat sempre és la velocitat de càlcul. Per tenir més potència de càlcul, el que tenim és tota aquesta fila d'aquí i aquesta d'aquí. Això són els nodes computacionals. Són molts, són més de 3.000, 3.456. Però perquè tots ells treballin a la vegada, la part més important, després ho veureu al tour virtual, és la part central, que són els routers, és la xarxa. Necessitem una xarxa, una fibra òptica que connecti tots aquests ordinadors de forma molt, molt ràpida. D'acord? Què més tenim? Perquè això funcioni, doncs necessitem tenir un aire més o menys fresquet dins del site, necessitem refrigerar-ho. Tota aquesta fila lateral i aquesta d'aquí, això és la refrigeració. Això és el site. Això és, no us enganyaré, és ferro, molt maco no és. Bueno, sí, té llumetes verdes, té cables en colors i tal. Aquí el realment espectacular, ostres, és aquest entorn. O sigui, aquesta caixa de vidre, aquesta peixera, està dins d'una església, una capella. La capella no és molt antiga, és de 1950, del Pego, però només té 70 anys. Això realment va ser un convent de monges. O sigui, va treballar com a església fins a l'any 77, que va passar a la universitat, a l'UPC, Universitat Politècnica de Catalunya. Va venir el bisbe de Barcelona, la va desacralitzar, no és cap heregia posar la màquina aquí, i fins a l'any 2004 va donar serveis a la universitat. Llavors, el primer ordinador que vam posar, que vam instal·lar aquí, va ser l'any 2004, d'acord? I hem anat creixent fins a l'actual. La màquina, suposo que si no ho sabeu, us comento, existeix un rànquing que es diu Top 500, que ens ordena els 500 ordinadors que hi ha en el món, els 500 més potents que hi ha al món. Diuen que no hi ha cap altra màquina amb aquest rànquing en un lloc com aquest. Bueno, més ràpida la màquina per estar dins de l'església no és, però és més maca de visitar, no té més. Ens aprofitem el tema d'estar aquí dintre per ensenyar una mica temes de la màquina, d'acord? Bueno, una frase com a introducció, sempre m'agrada molt comentar que no hi ha res més al món que faci avançar la ciència com l'aplicació d'un nou instrument. I això es pot aplicar a moltes coses, a instruments, a softwares, a el que sigui. Moltes vegades se'm pregunta per temes dels ordinadors quàntics. Abans parlàvem amb el César, que un quàntic, com farà uns, no sé, 7, 8 anys, era totalment ciència-ficció dins del món de les idees. Actualment ja començam a tenir alguna cosa palpable, no és 100% operable, no és 24%, però ja existe. La tecnologia avança tan ràpidament que poder d'aquí 4 o 5 anys hi ha un avanç tecnològic que ens fa que el quàntic pugui ser molt més útil que ara. Ara li veiem l'utilitat, però encara no ens és útil. Doncs no hem de tancar les portes a això. Si el quàntic pot ser que sigui algo útil, a per ell. O sigui, Mare Nostrum per nosaltres, ja ho diré després, no és més que una eina. Per tant, si el quàntic pot anar bé per la investigació, hem de començar a tenir-lo en compte. Tenim un quàntic nosaltres de 2 qubits. El quàntic més potent del món en té 54. Hem de començar a fer petits experiments per veure si això després ens pot ser útil. No sé, coses... A ningú se li escapa que la utilització, per exemple, del periscopi en el món de l'astronomia va ser un antes i un després. De veure les estrelles amb els nostres ulls a veure-ho amb un telescopi o al món de la medicina, un microscopi. Va ser poder començar a dissenyar, a veure les bactèries, a dissenyar fàrmacs gràcies al microscopi. I actualment, l'ús de supercomputadors o de artícules. Per què utilitzem un supercomputador actualment? A qualsevol àrees molt, molt, molt grans, tot el que té a veure amb enginyeria. Però jo diria que qualsevol àrea de la ciència actualment pot fer servir un supercomputador. Vamos al meollo. Mare Nostrum és l'eina més important que tenim al BSC. És una d'elles. Nosaltres sempre remarco molt, som un centre de recerca. El nostre principal objectiu és fer recerca. Actualment som uns 800 persones treballant al centre. Penseu que el centre es va crear el 2004 i érem 30 persones. O sigui, de 30 hem passat a 800 en 16 anys. Brutal. I pel mig hem tingut una època de crisi molt bèstia a Espanya. O sigui que d'aquests 800, diria que prop dels 600 som investigadors. Més del 80% del personal del centre es dedica a investigar. Per tant, el que deia, Mare Nostrum està molt bé, és un ordinador molt potent, és molt maco de veure, però per nosaltres no deixa de ser una eina per poder millorar, per fer millor la nostra recerca. Llavors, en temes de recerca, el que fem és, tenim la màquina com a objectius, tenim recerca interna, ara us comentaré els grups d'investigació que tenim aquí al centre, però al tenir aquesta màquina ens permet també donar suport a centres de recerca externs, prioritàriament investigadors espanyols o europeus. No estem tancats, tenim projectes amb la NASA, amb Silicon Valley, amb Japó, amb Brasil, però la prioritat, el finançament, ens arriba del govern espanyol i de la Comunitat Europea. O sigui, és o recerca externa o recerca interna. El que deia abans, prioritàriament és recerca. Després tenim com a tercera pota el tema social i educacional. Fem molts cursos de postgrau, cursos d'estiu, cursos específics de supercomputació, paral·lelisme, d'ús d'eines, d'anàlisi de dades, el que sigui. I el tema de transferència de tecnologia. Això és molt important. Penseu, molta gent quan pensa en temes d'investigació sempre pensa que la meca és als Estats Units. No van desencaminats, però a Europa estem fent, en quant a recerca, en alguns camps, tan bona com els Estats Units. El gran problema que té Europa és que després el que s'investiga es queda en l'empresa pública. No tenim aquest traspàs de la pública a la privada. I aquest és un gran problema. Nosaltres tenim un grup d'investigació que vam crear el 2008 que es dedica a això, a treballar amb empreses per poder fer el que es diu la transferència de tecnologia. Penseu que en els últims 5 anys, la setmana passada vam presentar l'última startup creada al BCC, en 5 anys hem creat 11 startups. Estem superorgullosos. 11. Això hauria de ser als Estats Units cada dia, però bueno, s'ha de començar. O sigui, és el gran problema que té Europa. No tant la recerca, sinó el com traspassem aquesta recerca a l'empresa. Bueno, doncs aquests són els 4 grups d'investigació que tenim. Són 3 grups purament d'investigació 100%, Computer, Earth i Life Science, i el grup de CASE, que és el que us he dit, que és el grup que treballem amb les empreses. Computer, bàsicament, el computer és el nucli dur. O sigui, el BCC es va crear el 2004, però diríem que des de l'any 90 ja estem fent coses de supercomputació. Bàsicament amb aquest grup. Vam començar a la Facultat d'Informàtica de Barcelona, un grup de recerca dins del Departament d'Arquitectura de Computadors. Computer Science el que fan és dissenyar o influenciar com seran els processadors del futur. Com seran de hardware, però molt més important, com els podrem utilitzar. És un altre dels grans problemes que tenim a Europa. La transferència, com he dit abans, i el disseny de processadors, que se'ns ho estan menjant tot, els americans, xinesos i els japonesos. La Champions League són aquests 3. Europa està al darrere. Intentamos llegar, però encara no arribem del tot. I en relació a tot això tenim tots els temes de projectes d'intel·ligència artificial, temes de Big Data, de Smart Cities, tot això. Earth Science. Earth, bàsicament, el que fan són 2 grans projectes. Un que és el tema del canvi climàtic. Penseu que fins ara els models dels canvis climàtics que fèiem les prediccions eren a centenars d'anys, a llarg termini. Què ens passarà aquí a la Terra d'aquí 500 anys? Això, la gent, per un lado entra i per l'altre sale. Actualment, les previsions que tenim ja és a mitjà termini, ja podem preveure què passarà d'aquí 20-30 anys i això ja és molt important, perquè socialment això ja ens arriba. A mi 20-30 anys, con suerte, però els meus fills sí. I la gent ja comença a estar més sensible amb el tema del canvi climàtic. I molt important, els polítics. O sigui, ja el nostre missatge està arribant als polítics que amb això, gràcies a aquests temes, a aquests models que estem creant, poden canviar polítiques socials i ecològiques. L'altre gran projecte que tenim a Earth és el tema de qualitat de l'aire. Contaminació. Bàsicament és medir la contaminació que tenim al nostre entorn i fer prediccions als propers dies. Això es va començar per grans ciutats. Tenim un gran problema a Europa, tant a Barcelona com a Madrid, i Amsterdam i París, i tot. Grans ciutats europees tenen problemes de contaminació. Llavors va començar aquí i ara mateix tenim un app, l'IOP, gratis, podeu baixar-la al vostre mòbil i ja podeu fer la previsió als vostres pobles, a tot Catalunya, a tot Espanya, fins a tota Europa. I Life, diríem que és tot el que té a veure amb bioinformàtica. Diríem tot el que fa Life va encaminat al que es diu la medicina personalitzada. O sigui, el futur és no crear fàrmacs a lo gordo, sinó crear coses que incideixin a cada un de nosaltres. Aquesta presentació, aquesta divisió de grup de recerca és una mica antiga, dels 2000. O sigui, no és cert que la recerca sigui només amb gent de computer, només amb gent d'Earth i només amb gent de Life. Aquí la recerca actualment és sempre totalment transversal. Si estàs fent el disseny d'uns fàrmacs, per exemple, la Covid, ara tot el tema del Covid se'ns està menjant i hi ha molts projectes del BCC relacionats amb això. Des de com es va crear, com està desenvolupant i temes farmacològics. A Catalunya tenim molt present que hi ha 2 grans projectes, el d'Irsi Caixa i els dels Grífols, del laboratori de Grífols. Amb els 2 estem treballant, fent recerca conjunta i a l'hora de fer servir la potència de càlcul fem servir Mare Nostrum. En el cas del disseny dels fàrmacs es fa servir intel·ligència artificial. En aquest cas estem fent servir gent de computer que treballin amb aquesta gent. O sigui, tot sempre ha de ser totalment transversal. I la gent de Case és la que us he comentat, que són els que estan connectats amb les empreses. O sigui, estem projectes comuns entre els nostres investigadors de... Bueno, anem a lo que és la màquina. La màquina es diu Maelstrom 4, originals, és la quarta versió, hem fet Maelstrom 1, Maelstrom 2, Maelstrom 3, Maelstrom 4, i ara ja estem pensant en fer Maelstrom 5. De fet, ja l'hauríem d'haver tingut. O sigui, la planificació era novembre del 2020 tenir Maelstrom 5, problemes Covid doncs ha fet que això es retraci i tindrem el primer quatrimestre, els primers 4 mesos del 21, ja tindrem la primera fase de Maelstrom 5 en marxa. Nosaltres sempre tenim dos tipus de màquines. Una, la propòsit general, que és la gordota, que serveix per qualsevol tipus de càlculs. I després tenim altres màquines més petites, que són noves tecnologies, que són les màquines que fem servir per avaluar aquestes tecnologies i aviam si alguna d'elles potencialment ens serveix per les següents versions de Mare Nostrum. De fet, si veieu aquesta primera, aquesta és de l'any 2018, ja té 2 anys. Doncs aquesta és una de les solucions que estem pensant per Mare Nostrum 5. No us puc dir quina serà la solució final perquè encara està en concurs, s'ha d'obrir el concurs, s'ha de resolucionar, però una de les propostes era aquesta. P9, fixeu-vos que la màquina més potent del món del novembre del 2019 era una màquina amb P9, és processadors Power 9, és el processador potent d'IBM genèric, de gamma alta, i Volta és una targeta gràfica d'NVIDIA. Això són màquines molt, molt específiques. Específiques vol dir que poden ser pel mateix preu més barates, més potents, perdó, pel mateix preu poden ser més potents i més eficients. Però són específiques. Específiques vol dir que serveixen per poques coses. Per aquestes poques coses volen. Bueno, el que he dit abans, Champions League, o sigui, màquines com aquestes que pot tenir molt, molt potents, Estats Units, Xina i Japó. Estamos en Espanya. A Espanya només tenim 2 màquines al top 500. La més potent d'Espanya és aquesta primera, i la segona més potent d'Espanya és aquesta segona. Per tant, hosti, com anem a una màquina, o sigui, amb el mateix preu, amb el preu que vam pagar 38 milions d'euros que va costar Maelstrom 4, si haguéssim fet una màquina amb Power 9 i voltes, tindríem una màquina de possiblement 30 petaflops, el triple, entre el doble i el triple. Però només serviria per pocs projectes. Per tant, s'ha de valorar-ho tot això. Llavors també tenim ara actualment altres 2 processadors, 2 màquines, una processadors ARM, ARM són els processadors que tenim als mòbils. Aquest és un projecte que vam iniciar aquí al BSC l'any 2008 i això ha anat evolucionant i actualment la màquina més potent del món, des del juny del 2020, està al Japó i utilitza aquesta tecnologia. És una màquina de 400 petaflops ja. O sigui, Déu-n'hi-do. Doncs nosaltres tenim una petita màquina d'aquest estil, la tenim instal·lada des del febrer del 20, ens va arribar el Nadal, però l'acaba d'instal·lar al febrer. I el mateix, ja estem jugant amb ella, avaluant-la, però amb vistes ja no Maelstrom 5, sinó amb vistes de Maelstrom 6. O sigui, no tenim la 5ena i ja estem pensant com serà la següent versió. D'acord? I l'altra màquina d'AMD, penseu que, fixeu-vos aquí baix, això és l'evolució de les màquines, estem parlant de teraflops, de petaflops. La carrera que hi ha ara en supercomputació és aviam quin país arriba abans a l'hexaflop, a 1.000 petaflops. El teraflop va ser als Estats Units, el petaflop va ser als Estats Units i per l'hexaflop el roadmap que tenim és que tant els Estats Units com Xina l'any que ve arribaran a l'hexaflop. Xina no se sabe com, és totalment tecnologia pròpia i top secret, i als Estats Units ha apostat, el concurs que ells han fet, ha sigut una màquina amb processadors AMD, igual que els tenim aquí. Nosaltres tenim aquí una de 0,52 i ells faran una de 1.200. Però bé, per el mateix, ja comencem a avaluar aquesta tecnologia, aviam si per d'aquí 4 anys ens pot ser útil per nosaltres. D'acord? I Japó, la idea és tenir l'hexaflop al 23. El que passa que ningú es pensava que aquest juny tindria la màquina més potent del món. Jo crec que s'avançaran, no arribaran l'any que ve, però potser d'aquí 2 anys sí. Bueno, què utilitza la màquina? El 20% de Mare Nostrum és per l'ús dels investigadors propis del centre, un altre 20% per investigadors de caire espanyol, de l'Estat, i un altre 60% d'investigadors europeus. Aquest 80%, tot és totalment competitiu. O sigui, nosaltres no escollim qui pot utilitzar, sinó això va parar un comitè, aquest comitè avalua tots els projectes i els va repartint hores segons l'important que sigui. FAIRE és una xarxa a nivell europeu que són 7 màquines. Hi ha 3 a Alemanya, la de França, la d'Itàlia, la de Suïssa i la nostra. Aquestes 7 màquines el que fan és donar suport a tota la recerca europea. O sigui, això és un win-win. Jo cedeixo part de la meva màquina, però les altres també. Jo, com a investigador espanyol, investigador del BSC, podem demanar utilitzar part de les altres màquines. Com he dit abans, competitivament, jo utilitzaré la de Jülich, que és la més potent d'Europa actualment, si el meu projecte és més important que la resta. Estem intentant jugar a fer la recerca europea millor possible. D'acord? Futuro, què ens espera? Doncs el que deia, o sigui, Manestrum 5 és una màquina de 200 petaflops. És 20 vegades la que tenim actualment. Penseu que fins ara les màquines que hem tingut són financiades pràcticament pel govern espanyol, però eren màquines, l'última eren 38 milions d'euros. Aquesta, la inversió és més de 200. Més de 200 milions d'euros. Això és gràcies a un projecte de caire europeu que Europa ha apostat, no estem al top 3, però el que volem és començar a fer una mica nosa, una mica la guitza. Llavors, per aquest any es va obrir un concurs i instal·larà a Europa 3 grans màquines. Una, el concurs la va guanyar Finlàndia, l'altra Itàlia i l'altra nosaltres. Les 3 són màquines pre-hexaflops. Ja no arribem a l'exaflop encara, però seran les prèvies, més de 200 petaflops cada una d'elles. 50% d'aquesta màquina està financiada pel govern, per la Comissió Europea, i l'altre 50% la financien, en el nostre cas, els governs de Croàcia, Turquia, Portugal i Espanya. Aquests 4, els investigadors d'aquests països, tindrem un percentatge prioritari d'ús. D'acord? He anat una mica ràpid, perquè el que també m'interessava, entenc que la història era ensenyar-vos el tour virtual. Si aneu a la nostra pàgina web, ha de tenir aquí. Si aneu a la nostra pàgina web, a la part de baix aquí teniu el que diu visita virtual. Si cliqueu aquí, anireu a petar a una eina, es pot fer en català, castellà, anglès, com vulgueu. És una eina molt xula. El que vull aquí és presentar-vos, és ensenyar-vos-la perquè després cadascú al seu aire, quan vulgui, entri. Pots estar molt de temps, moltes hores treballant, visitant la màquina. Aquests són els jardins del campus d'on treballem. És un lloc força xulo per treballar, no enganyo, està bé. I això és la capella. Això és la part del darrere de la capella. Aquesta és la nostra mascota, la Supergeek. Si entreu aquí dintre, doncs podeu entrar i navegar pas a pas, podeu començar a visitar la màquina, els entorns, això és el que és el foyer, el hall de l'entrada. Ens trobarem, farem la visita en 2 plantes, la planta de baix, que és aquesta d'aquí, i després pujarem a la primera planta. Ens trobarem sempre cercles de color gris. De color gris vol dir informació o genètica, com en aquest cas, diu que estem entrant a el que és el Mare Nostrum, o informació tècnica de la màquina. I a la part de dalt veureu cercles de color vermell. Vermell vol dir informació de recerca. Doncs podem anar entrant. Això ja, jo entenc que la primera vegada que entreu fareu tot el passadís, anireu mirant punt a punt, i anant mirant. Aquí hi ha uns punts molt macos, es pot veure molt bé. És una eina molt potent. Si cliqueu aquí baix, aquí hi ha un play. Si sou molt mandrosos, feu el play i fa la visita directa tota. D'acord? Si no, podeu anar directament també als punts en particular. Dius, ostres, la primera vegada ja dic, entenc que el que fareu és pas a pas anar fent una visita de guia de vosaltres mateixos, però si voleu anar a un punt en particular, doncs podeu anar. La idea és, entrarem per aquesta porta d'aquí i sortirem, acabarem per aquesta d'aquí. Serà una visita circular. El que us deia, teniu molta informació, aquí teniu aquesta, jo crec que és la de l'slide que he fet abans, sí, l'evolució de la màquina. Aquí teniu per xafardejar moltes coses a mirar. Entreu aquí dins, això és l'àbside de l'església, aquí és on el sacerdot feia missa. Veieu l'entorn, més el zoom aquí, sí que el que feia abans, si es pot veure, amb molta claritat. Teniu aquí és una placa, aquí és un vídeo, els vídeos millor que cadascú pel seu compte, perquè si no l'amplada de banda se'ns ho menjaria i aniria així a trompicones. És un vídeo d'explicació del que és la màquina. Entre altres coses, estem fent això avui, ja ho sabeu, pel tema Covid. La visita a la màquina és totalment de franc i es pot fer presencialment. Ara s'entén que no, però cuando todo pase, si algú vol venir, l'explicació ja l'hauré fet una mica, però us podem ensenyar a l'entorn. Amb una visita presencial, el que fem és anar per aquest lateral d'aquí. I mirem la part de baix, que és el terra tècnic, des del lateral. 4 grapes. Però, tot és perquè aquí dintre, és on està el site, és territori prohibido, allà no es pot entrar. Allà només entren els sysadmins, la gent que s'encarrega que la màquina funcioni. Estem en una visita virtual, per tant no farem malbé res, doncs podem entrar. Entrem aquí dintre i podem fer la visita dins del site. Com us he dit abans, la primera fila, tot això d'aquí són discos. Són 5 racks plens de discos, aquí veieu els discos que hi ha, físics, són 14 petabytes i tenim aquí un primer rack també de flash, són 400 teres, són 2 nivells d'accés, un molt ràpid de 400 terabytes i un altre rapidillo de 14 petes. Podem anar i visitar, aquí tenim molta informació, molts punts per mirar, aquí tenim una placa oberta, doncs vamos a por ella, mirem la placa, podeu veure realment els components de la placa que tenim aquí, el processador, la memòria, connexions, el disc, i aquí tenim una foto de la placa. Fixeu-vos que tenim 3.456 plaques com aquesta. Tenim 2 processadors Intel de 24 cors cada un. En total uns 180.000 cors. Què podem fer més aquí? Jo, perquè ja me lo conozco, però vosaltres el que heu de fer és començar a entrar, a navegar, racons i mirar on estan els punts d'informació. Fixeu-vos aquí sota. El que hi ha sota és el terra tècnic. Un rack d'aquests fa 2 metres d'alçada. Per sobre, fins al sostre de la urna, hi ha 2 metres més, són 4 metres. I aquí sota hi ha 1 metre de terra tècnic. Els sites són 5 metres d'alt. Si mireu aquí el 360, això és una foto molt xula del que hi ha aquí sota. Aquesta realment és la part més important del que és aquest site. Sense això no tindríem un supercomputador. Aquí hi ha uns 100 quilòmetres de cablejat. Primer nivell, aquest de color blau, més o menys blau turquesa, diuen, això és fibra òptica. Això és el que connecta totes les màquines, totes les plaques entre si. Això és el que permet que un sol treball, un sol projecte, pugui executar amb tots els racks de cop, amb totes les plaques. D'acord? Una vegada em pregunten, hòstia, jo he vist per Google, navegant, he vist el site d'Amazon o de Google i són més grans que aquests. Sí, són més grans. No són més potents, són més grans. Però no són més potents perquè no volen. Per pasta podrien tenir màquines més potents. Però és que l'objectiu que ells tenen és diferent que la nostra. Ells el que volen és tenir centenars de milers d'usuaris treballant a la vegada. Jo no. A mi el meu èxtasi seria que un sol projecte treballés amb tota la màquina. Això passa comptades vegades. Si a Google li dius que un sol projecte està treballant a la vegada, lo hundes, és la misèria. Per tant, el que aquí tenim és això d'aquí. Això és el que ens diferencia amb la gran majoria de sites de base de dades que hi ha per allà. Aquest segon nivell és xarxa gigabit, és per sysadmin, és per controlar la màquina, purament gestió. Tirem un altre cap a fora, nosaltres hem vingut, aquí és l'entrada, aquí és la placa, doncs per l'altre lado. Si tirem enrere, seguim fent, podem veure això, totes aquests armaris aquí n'hi ha 3 com aquest, 1, 2 i 3, són els 3 armaris de fibra òptica, els routers. O sigui, tota la xarxa que hi ha aquí sota passa per aquests armaris d'aquí. Aquí crec que n'hi ha un altre, sí, aquí. us recomano que mireu aquí aquest punt, hi ha un vídeo, que és un timelapse, de com es va crear Marenostrum 4. Penseu que el site, fins ara, fem servir el mateix. Això què vol dir? Que quan instal·lem Marenostrum 4, aquí hi havia Marenostrum 3. El primer que ha de fer és agafar tots aquests racks i per fora. Després agafar tota la xarxa que havia aquí a baix i per fora. Hi ha un moment del vídeo que es veu tot el terra ple de xarxa de color vermell, tot, pam, tot ple. És la fibra òptica que teníem abans. Després entra la fibra òptica nova, després entra els racks nous i després un altre cop tira els cablejats cap a dalt. 3 mesos de feina, un vídeo de 2 minuts. Diria que més de 2 mesos estan relacionats amb tema de cablejats. És impactant. Ja podem sortir per darrere. Això és la porta principal de l'església, per on la gent entrava a fer missa. I aquí tenim la part, la vista des del darrere. El que us deia, aquesta fila d'aquí és Mare Nostrum i aquesta d'aquí. I aquí al mig, això són 2 racks que són el que hem comentat abans de les noves tecnologies. Aquí tenim el processador Power nou amb GPUs. Màquina i màquina, 2 tipus diferents de màquines. Tema refrigeració. La idea és que, normalment la idea que tenim quan entrem a un site és, hosti, fa molt de fred, entrem amb jerseis i tal. Des que hem fet Marenostrum 3 això ho hem canviat. Aquí dintre la temperatura homogènia a tot arreu és 23 graus. Veranillos, està molt bé, confortable, fa molt de soroll, però la temperatura està molt bé. Què passa? Problema. Sempre es refrigera per davant, ok? Si li entrem 23 graus per aquí davant, això va passant per la placa, pam, i mentre va passant es va escalfant. Veieu que aquí al darrere, faig un altre cop el zoom, això aquí és una porta ben gruixuda, quasi bé un pam. Aquesta porta, si l'obres, sortiria un xorro d'aire, no sé, a més de 50 graus, una bufetada. Però si la tanques, he dit abans que és homogeni, màgia, surt un altre cop a 23 graus. Per què? Això no es veu massa bé, em sembla. A la part de baix, inferior, aquí es veu una mica, s'intueix, veieu que hi ha uns tubs de color negre? Aquí es veu una mica més. Aquests tubs estan a tot arreu. Tots aquests armaris, per sota hi ha uns tubs negre que el que fan és connectar aquesta unitat d'aquí amb totes les portes. I això és refrigeració per aigua. Estem posant aigua freda a totes les portes del darrere. D'acord? Tot això són tubs plens d'aigua freda. Un refrigerador, amb portes fredes. Què passa? Que l'aire que hi entra a 23 s'escalfa fins a 50 i pico i a la travessar la porta freda torna un altre cop a 23 graus. Tot això és bàsicament per un tema energètic. El gran problema d'aquestes màquines és el consum energètic. Penseu que cada any estem gastant del voltant d'1,5 milió d'euros. Amb aquest canvi vam reduir un 10%. És poc? Bueno, són 150.000 euros que en vam estalviar. Ja està bé. Aquí anem cap a dalt, després baixarem per les escales, que estan aquí al final, però per pujar anirem més ràpids i pujarem per aquí, directament a la finestreta i ja estem a dalt. A dalt podem anar tot aquest passadís, veure la màquina pel costat, hi ha un pont que travessa la màquina per dalt, per sobre, és molt xulo. Aquesta vista és superguapa. Mira, he saltat com a Superman, és una de les coses que ens pot permetre també fer aquesta eina, cosa que amb una normal no pots fer, doncs aquí sí. No volia fer, se m'ha ido. Veus, aquesta és la vista. Tenim els 2 passadissos amb els seus arcs, aquí davant això és l'àbsid, un altre passadís, i a sota tenim la màquina. Jo crec que és una vista molt maca aquesta. El que us deia abans, tots aquests cercles de color vermell, aquí baix, tot això són vídeos de recerca. Vídeos curtets, cada un és un vídeo. I aquí dalt tenim 3 vídeos de recerca més genèrics. Jo sempre en una visita presencial els ensenyo aquest d'aquí, de l'esquerra, són 12-15 minuts, que us ensenya 8 projectes que estan treballant a Mare Nostrum. D'aquests 8 hi ha 7 que encara treballen i un que està en fase final, d'energia eòlica. Són projectes de llarg termini. I és molt xulo perquè visualment és molt maco de veure, però també et dona una idea de per què serveix un supercomputador, quin tipus de projectes estem fent servir aquí. També tenim a la part del darrere, això és el corus de l'església, normalment aquí poso gent, aquí veieu que hi ha uns projectors, Aquí hi ha unes pantalles, val? Aquí faig la xerrada, faig xerrades per aquí. Val? I si anem a l'altre costat, ja arribaré ara. Veig aquesta porta, indica que aquí al darrere, pronto, espero que muy pronto, tindrem Manestrum 5. Val? Això és un pont que connecta aquest edifici amb un que tenim a 10 metres, aquí al costat. Què passa? Fins ara us he dit, amb el timelapse que us he dit que mireu, després quan tingueu temps, que sempre utilitzem el mateix site, el mateix espai. Val? Però clar, cada cop que hem actualitzat la màquina hem multiplicat per 3, per 4, una vegada per 9, però clar, van passar 7 anys. Ara, en 3 anys i mig, multiplicarem per 20. És una brutalitat. Val? Què vol dir? Que amb aquest espai d'aquí, la màquina nova no hi cap. Val? Això són 200 metres quadrats. A l'edifici nou tenim 1.000 metres quadrats de planta. No els utilitzarem tots i està pensat per fer properes actualitzacions en el futur. D'acord? Doncs, una cosa bona, no tindrem l'església per ensenyar la màquina, però el que sí és que tindrem 2 màquines per poder fer recerca. I penseu que quan tinguem Manestrum 5, tindrem Manestrum 5, però seguiríem tenint Manestrum 4 aquí sota. A més, durant el 21. Després, ja veurem si part de la màquina se'n va a altres centres d'Espanya. Però en un principi tindrem 2 grans màquines per utilitzar. Bueno, ja acabem. Anem a baix. Ara sí que anem per les escales, xino-xano, poc a poc, sin caer-nos. És el que podíeu fer, cadascú. Ja entrant, mirant. I per acabar, aquí tenim un passadís. Aquí podem mirar per aquesta finestra, em sembla que es veu. Aquest edifici de color blanc, aquest és l'edifici nou. Aquí és on tindrem Mare Nostrum. És una foto feta al juny, per això encara estaven fent obres. I aquí és el passadís, és una espècie de museu. Són les màquines antigues que teníem en el nostre centre. Estan ordenades de la més nova a la més antiga. Aquesta d'aquí, la més nova, és un armari de Mare Nostrum 3. Aquí tenim la fitxa tècnica, aquí els líquids informàtics, aquest passadís s'hi passen estona. Hi ha gent que ho fa de visita que és pim-pam, entren i salen, i els que realment els encanta la informàtica i han treballat, que ja tenen poco pelo com allò, ja comencen aquí i s'hi passen l'estona mirant tota l'evolució de les màquines que hem tingut. L'última de totes, aquestes 2 últimes, ja com aquestes, no patiu. Aquestes són, nosaltres sempre, el que he dit abans, sempre tenim 2 tipus de màquines, la genèrica i la d'investigació. Doncs l'any 91-92, aquesta aquí al final, aquest cub de color negre tan xulo i tan modern, era la màquina d'investigació, era una nova tecnologia. I en canvi aquesta aquí era la genèrica. Però fixeu-vos, una placa enorme, són uns 4 pams, i de fondo deu tenir uns 6 pams. Aquí hi havia un processador. Teníem 8 plaques com aquesta. Si mireu la fitxa tècnica, aquesta era la màquina més potent que havia a Espanya, ens va costar $1 milió i mireu la potència. No arriba a 1 gigaflop. El vostre mòbil és més potent que aquesta màquina. O sigui, fa 28 anys, la màquina més potent d'Espanya era menys potent que el mòbil que tenim avui en dia. O sigui que realment, si aneu per aquí passejant, ara aquí ja xulo perquè aquesta màquina s'aixecava i aquí quan existien els processadors, quan estaven, eren tot de leds de color vermell, s'encenia i s'apagava i era molt maca. He anat molt ràpid, però és que teníem el temps que tenim.
Sí.
Tot vostre, preguntes, digueu-me, dudas.
Pues por aquí nos ha llegado alguna pregunta, pero estamos súper cortos de tiempo, Oriol. La verdad es que me pasaría dando vueltas.
Yo he ido acelerando porque me estoy quedando mal de tiempo.
Sí. Por aquí Carmen Sex nos pasa una pregunta, pero como justo nos están esperando para pasar una performance, la voy a lanzar y le voy a invitar a que haga este tour. Porque sí que es cierto que este tour está disponible. Nos preguntaba si el circuito de refrigeración de las puertas es un circuito cerrado. A mí también me llama mucho la atención el circuito de refrigeración líquida. Seguro que hay más información en todos esos puntos que nos hemos quedado por el camino. Me ha parecido una visita muy interesante y un esfuerzo en la línea justo de lo que comentabais, de divulgar lo que se está haciendo, de darlo a conocer y de invitar a la gente a pensar en la computadora a gran escala, ¿no? Que a veces pensamos como pequeños procesos, ¿no? Pero se abre todo un nuevo universo de posibilidades con lo que hacéis allí en Mare Nostrum. Y nada, estaremos pendientes. Mare Nostrum 5, el año que viene ya nuevas instalaciones, nuevo edificio, todo funcionando a la vez. Me ha parecido espectacular. Así que nada, os doy la enhorabuena y también de parte de la gente que está ahora mismo viéndonos aquí en Maker Faire Girona. Invitaros también, si estáis viendo hoy, que no os vayáis todavía. Vamos a tener una performance ahora muy tecnológica, porque vamos a ver un grupo que se llama Ensemble Topographic, en el que básicamente combinan la música y la tecnología para poder llevar el arte de una forma muy visual. Es un colectivo, son dos personas, Ana Hierro, que es bailarina, y Carlos Martorell, artista sonoro y visual. Y, como os digo, en la presentación nos vamos a fijar en la parte estética, pero me chivan desde la nave nodriza, que todo lo sabe de la computación, que tanto Ana como Carlos llevan sensores en sus brazos y cámaras que captan el movimiento. Así que todo lo que vamos a ver en pantalla lo vamos a ver como una mezcla, como una especie de sinestesia maravillosa en el que la tecnología y el arte se mezclan de una forma única. Y esto es todo por hoy aquí en Visiting Spaces. Seguimos aquí en Maker Faire Girona mañana. Espero que lo estéis pasando bien. Seguiremos viendo sitios tan interesantes como este de BSC. Gracias, Oriol, por tu tiempo y por acompañarnos hoy. Y como os digo, ya mismo pasamos a la performance aquí en Maker Faire Girona. Hasta mañana.
Pues
Hola.
muchas gracias.
Nada, Oriol.